Welcome to Astro Odyssey. Explore the universe. For millennia, humanity has gazed skyward, wondering what lies beyond our terrestrial home. It is a fundamental impulse, this urge to explore, to push boundaries, to discover. This is not a modern phenomenon, nor is it a product of the industrial age. It is written into the very sequences of our DNA. Evolutionary biologists often point to the EARD for 7AR genetic variant linked to restlessness and curiosity as a possible marker for our species' unique compulsion to wander. While other apex predators are content to dominate a specific niche, humans are biologically programmed to seek the other. When our ancestors first looked across the Great Rift Valley, they did not see a horizon that marked an end, but a challenge that demanded a beginning. The valley was not just a geographic feature, it was the first crucible of the human spirit. Those who stayed behind in the familiar groves often survived in the short term. But those who moved, those who crossed the ridge, were the ones who ensured the species' adaptability. From the first tentative steps out of Africa to the grand voyages across the trackless, terrifying expanses of the Pacific and Atlantic Oceans, our history is a testament to an insatiable curiosity and a relentless drive to expand. We are a species of the beyond. We are the only creatures on this planet that consistently refuse to be defined by our geography. Unlike the migratory birds that follow the same magnetic ley lines for eons, we choose our destinations based on imagination rather than instinct. We built outrigger canoes to find islands we didn't know existed. We built sextants to navigate by stars we couldn't touch. This restlessness served us well in the Pleistocene, pushing us to find better hunting grounds and more stable climates. It served us in the age of discovery, mapping the hidden corners of the globe. However, that era of horizontal expansion has reached its natural conclusion. Today, the maps are full. Every mountain has been measured by satellite. Every trench in the sea has been echoed by sonar. We live in an age of the end of geography. For the first time in human history, the frontier is no longer a horizontal line across the earth. It is a vertical ascent into the black. This shift represents a fundamental change in the human psyche. When we explored the Americas or the Antarctic, we were still breathing the same air, protected by the same magnetosphere. The vertical frontier is different. It is an environment fundamentally hostile to our biology. To cross it is to acknowledge that we can no longer rely on the passive hospitality of our birth-world. We stand now at the precipice of our greatest journey yet, the colonization of the solar system. This is the transition from a planetary species to a multi-planetary one, a biological leap equivalent to the moment the first lungfish crawled onto a muddy shore. Consider the 375 million years since the Devonian period. The transition from sea to land required the evolution of lungs, the hardening of skin, and the structural reinforcement of bone to combat gravity. Our transition to space requires the technological equivalent of those biological adaptations. We are building metallic carapaces in the form of spacecraft and artificial lungs in the form of life support systems. But why? Why pour immense resources, the finest intellects of our generation, and the staggering wealth of nations into such a monumental undertaking? The reasons are multifaceted, born from both a cold, hard necessity and a soaring, romantic aspiration. We do not go because it is easy, nor do we go simply because it is there. We go because the cradle of Earth, though beautiful and bountiful, is a fragile vessel in a violent universe. We live on a planet that has experienced 5 mass extinction events. From the Permian-Triassic Great Dying to the Chicxulub impact that ended the reign of the dinosaurs. Earth's history is a ledger of catastrophes, To stay on a single planet is to place all our eggs in one cosmic basket. A single rogue asteroid, a massive solar flare, or even our own technological hubris could silence the human story forever. To leave is to ensure that the flame of human consciousness, which took billions of years to ignite, is never extinguished. By a single stroke of cosmic misfortune, Earth is the cradle of humanity, but one cannot live in a cradle forever. Konstantin Tsiolkovsky's argument for colonization begins with the most basic law of nature, survival. To look at the Earth today, a vibrant blue-green marble teeming with life, is to see a snapshot of a temporary peace. We perceive the planet as a stable, eternal home because the human lifespan is a mere heartbeat in geological time. But the rocks beneath our feet tell a more violent story. Earth is a paradise, but it is a paradise with a history of extinction. We live on a planet that has seen 5 major extinction events, where 99% of all species that ever lived are now gone. The fossil record is not a story of progress, a graveyard of the almost successful. The great dying of the Permian period saw the loss of 96% of marine species. It was not a slow decline, but a biological collapse triggered by massive volcanic eruptions in what is now Siberia, leading to an atmospheric greenhouse effect that literally cooked the oceans. To believe that humanity is exempt from this cycle is not optimism, it is hubris. We assume that because we have split the atom and mapped the genome, we have graduated from the school of natural selection. Yet, the cosmos remains indifferent to our achievements. By confining the entirety of our species to a single planet, we are placing all our evolutionary eggs in one basket. Consider the impact risk. The Chicxulub asteroid, which ended the reign of the dinosaurs 66 million years ago, was roughly 10 kilometers in diameter. It struck with the force of 100 million megatons of TNT. If such an object were detected today on a collision course with Earth, we would realize, with terrifying clarity, that our borders, our stock markets, and our digital clouds are illusions. Only a species that has established self-sustaining outposts on Mars, the Moon, or in O'Neill cylinders could ensure that the library of human knowledge and the spark of our DNA would survive the dust and the dark of a post-impact winter. A nearby supernova, a massive solar flare, a Carrington event on a global scale, or a rogue asteroid are not matters of if, but when. Furthermore, we must face the mirror of our own making. We are currently living through what biologists call the Anthropocene, the epoch in which human activity has become the dominant influence on climate and the environment. This is the paradox of our success. The very tools that allowed us to conquer the Earth are now the tools that threaten to destabilize it. Our success as a species has put an unprecedented strain on the biosphere. Our hunger for energy, space, and resources is outstripping the planet's ability to regenerate. We are currently consuming the equivalent of 1.75 Earths every year in terms of resources. This is not a sustainable ledger. Climate change, resource depletion, and the collapse of biodiversity are symptoms of a species that has outgrown its habitat. However, solution is not necessarily a retreat into the small is beautiful philosophy of the 1970s, which argued for a managed decline in human standards of living. Instead, the solution lies outward. Colonizing the solar system is not an escape hatch for the wealthy to flee a dying world, but rather a pressure release valve for the entire planet. Imagine a future where the heavy lifting of civilization, the smelting of steel, the manufacturing of semiconductors, the generation of gigawatts of power is no longer done in the thin, fragile envelope of our atmosphere. By moving heavy industry, mining, and energy production into the vacuum of space, where there is no biosphere to damage, no groundwater to pollute, and no air to poison, We can allow the Earth to heal. We can transition the Earth from a factory floor back into a garden. In this vision, the Earth becomes a protected heritage site, a planetary park where nature is allowed to reclaim the scars of the industrial age. The solar system offers us a bounty that dwarfs the resources of Earth. For centuries, we have fought wars over patches of dirt and trickles of oil. This Malthusian trap, the idea that population growth will always outpace resource production, is only true if you assume the Earth is a closed system. But the Earth is not a closed system. It is part of a neighborhood of unimaginable wealth. In the asteroid belt located between Mars and Jupiter, there are millions of fragments of the early solar system. A single M-type metallic asteroid, such as 16 Psyche, is a core of an aborted protoplanet. It is estimated to contain enough gold, iron, and nickel to collapse global commodity markets and provide for human infrastructure for 10,000 years. If we can harness even a fraction of the belt, the concept of scarcity becomes a relic of the past. If we could build cities in orbit with the steel of 1,000 mountains without ever digging a single new mine on the Earth's surface. On the moon, the soil regolith has been bombarded by the solar wind for billions of years, trapping an isotope known as helium-3. On Earth, this isotope is incredibly rare, yet it is the holy grail of nuclear physics. Helium-3 is a potential fuel for clean, second-generation fusion energy. Unlike current fission, or even deuterium-tritium fusion, helium-3 fusion produces no radioactive waste and can be converted directly into electricity. A few shuttle loads of helium-3 could power the entire United States for a year without a single gram of carbon emission. The colonization of space is therefore the ultimate environmental act. It is the outsourcing of our environmental footprint to the dead, empty reaches of the void. The vacuum of space does not care about heat waste. The radiation-soaked moon does not care about chemical runoff. We can utilize the dead parts of our solar system to sustain the living part. Finally, there is the philosophical imperative. We are, as far as we know, the only part of the universe that has become self-aware. We are the eyes of the cosmos. If life on Earth were extinguished, the universe would continue to exist. But there would be no one to witness it, no one to name the stars, and no one to wonder at the laws of physics. We carry a biological and perhaps even a cosmic duty to ensure that this flame of consciousness persists. The cradle of Earth served us well. It gave us the oxygen to breathe and the gravity to grow. But a child who never leaves the cradle never truly grows up. Our transition to the stars is the great maturity of the human race. It is the moment we stop being a passenger on a planet and start being the stewards of a solar system. The leap from exploration to colonization requires a fundamental shift in how we view technology. For the last 60 years, space travel has been a feat of disposable engineering, massive, expensive rockets that were used once and then dropped into the ocean like a spent soda can. This was the Apollo model, born of a Cold War sprint where speed was prioritized over sustainability. It was an era of monuments, not a movement of people. But we are witnessing the birth of a new era. The age of the permanent bridge, the advent of reusable rocketry, pioneered by a mix of private ambition and public cooperation, has dropped the cost of reaching orbit by an order of magnitude. When the first stages of rockets began landing upright on autonomous drone ships, the fundamental math of the universe changed. We moved from the expendable mindset of a luxury flight to the logistical mindset of a railroad. We are no longer building monuments to national pride. We are building the infrastructure of a new economy. To understand the scale of this shift, we must look at the cost per kilogram $kg. During the space shuttle era, it cost roughly $54,000 to send one kilogram of matter into low Earth orbit LEO. With the advent of modern reusable heavy lift vehicles, that cost has plummeted toward $1,500, and with the next generation of fully reusable megastructures, it is projected to drop below $100. At that price point, space is no longer the playground of superpowers. It is the domain of the entrepreneur, the researcher, and eventually the immigrant. The challenges are, of course, staggering. To live on Mars or the Moon, we must master the art of insight to resource utilization. ISRU is the science of living off the land. We cannot bring the Earth with us. The physics of the rocket equation, the brutal reality that you must carry fuel to lift fuel makes it impossible to ferry every gallon of water and every pound of oxygen from the surface of a deep gravity well like Earth. Instead, we must become cosmic alchemists. We must learn to harvest the ice hidden in the permanently shadowed regions PSRs of lunar craters. This ice is more than just water to drink. It is the oil of the solar system. By applying electricity to water to H2O plus 2H2 plus O2, we can crack it into liquid hydrogen for rocket fuel and liquid oxygen for breathing. The Moon, once thought to be a barren desert, is actually a gas station on the road to the rest of the stars. On Mars, the challenge is even more transformative. The Martian atmosphere is 95% carbon dioxide. Through the sabotage process, we can combine that CO2 with hydrogen to create methane, CH4, and water. This means the first pioneers on Mars won't just be explorers. They will be chemical engineers. They will bake the Martian regolith toxic perchlorotrich, destined to ceramic bricks for radiation-shielded habitats. They will use 3D printing rovers to print cities out of the very ground they stand on, using local sulfur and basalt as the ink. Beyond the chemistry of fuel and bricks lies the biology of survival. We must develop closed-loop life support systems, CLLs, where every drop of sweat, every exhaled breath, and every scrap of organic waste is recycled into the food we eat and the air we breathe. Right. On Earth, we have the luxury of away we throw things away. In a lunar colony, there is no away. This level of efficiency requires a revolution in controlled environment agriculture, CEA. We are developing hydroponic and aeroponic systems that can grow nutrient-dense crops in vertical racks, using 95% less water than traditional farming. We are engineering biological scrubbers, algae tanks that consume CO2 and produce oxygen at a rate 10 times higher than terrestrial trees. These technologies are not merely for the benefit of those living in the Shackleton crater or the Valles Marineris. These innovations will flow back to Earth, helping us solve the very problems of scarcity and sustainability that we face today. A water purification system designed to recycle urine into potable water for a Mars mission is exactly what is needed for drought-stricken regions in sub-Saharan Africa. The vertical farming techniques designed for the dark of a Martian winter are the solution to feeding a terrestrial population of 10 billion people on a shrinking footprint of arable land. In this sense, the colonization of the solar system is the greatest laboratory in history. In the harsh environments of the Moon and Mars, we will be forced to innovate at a pace that a comfortable Earth never demanded. Necessity is the mother of invention, and there is no greater necessity than an environment that is actively trying to kill you. We will reinvent medicine to combat the effects of low gravity and cosmic radiation. The research into preventing bone density loss in astronauts is already providing breakthroughs in the treatment of osteoporosis for the elderly on Earth. We will reinvent power too, harness the sun's rays without an atmosphere, pushing the efficiency of photovoltaic cells to their theoretical limits. Perhaps most importantly, we will reinvent the very concept of community. On a frontier where a single airlock failure can end a dozen lives, the social contract becomes more than a political theory, it becomes a survival requirement. The frontier effect has always been the engine of human progress. It strips away the calcified bureaucracies of the old world and replaces them with a culture of pragmatism, meritocracy, and radical cooperation. The vertical frontier is not just a destination, it is a catalyst, is the fire that will forge a new version of humanity, one that is smarter, leaner, and more resilient. We are not just going to space to save our bodies. We are going to space to sharpen our minds. Earth, her cradle, is beautiful and bountiful. A blue-green jewel suspended in the velvet dark of the cosmos. But it is not eternal, nor is it invulnerable. When the Apollo 8 astronauts captured the Earthrise photograph, it sparked a global environmental consciousness. However, that image contains a terrifying paradox. A world that feels infinite in its variety and life, yet appears as fragile as a soap bubble in a storm. From the perspective of the lunar surface, the atmosphere that we perceive as a vast, bottomless sky is revealed to be a thin, translucent membrane no thicker, relatively speaking, than the skin of an apple. For too long, we have treated our home as an inexhaustible well, a closed system that could absorb any shock. This flat earth psychology, the belief that the horizon goes on forever, and that our waste can be dumped into an infinite elsewhere, is failing us. The dawn of the 21st century has brought a harsh clarity to our predicament. We are hitting the walls of our nursery. We face growing environmental challenges that are no longer theoretical. A changing climate is not merely an abstract rise in temperature. It is a systematic reshuffling of the planetary deck. It reshapes our coastlines, threatens the breadbaskets of our continents, and forces a rapid depletion of the mineral and biological resources that built our civilizations. With burgeoning populations straining our planet's carrying capacity to its absolute limit, we are discovering that a single planet species is a species in a state of overshoot. Yet even if we were to achieve a perfect, sustainable utopia on Earth, even if we solved every war, ended every hunger, and balanced every ecosystem, the universe does not offer guarantees of safety. Beyond human-induced pressures, cosmic threats loom in the cold silence of the vacuum. We live in a cosmic shooting gallery, and while our atmosphere shields us from the pebbles, it cannot stop the mountains that occasionally cross our orbit. Our history is written in the craters of our neighbors. Look at the moon through a simple pair of binoculars, and you are looking at a chronological map of violence. Every pockmark on the lunar surface represents a collision that would have been a regional or global catastrophe had it struck the Earth. The only reason the Earth does not look as battered as the moon is that our weather, plate tectonics, and oceans erase the scars. But the scars are there. The Chicxulub event was just one of many. The Tunguska explosion of 1908 leveled 2,000 square kilometers of forest in an instant. Had that asteroid struck over London or New York, the course of human history would have been altered in a single morning. The threats are not only from without, they are from within the Earth itself. The very geological vitality that gives our planet its magnetic shield, the churning iron core that protects us from solar radiation, also harbors the seeds of destruction. We are a high-tech civilization built on a low-tolerance foundation, supervolcanoes. The sleeping giants beneath places like Yellowstone in the United States or Toba in Indonesia could wake at any moment. A supereruption is a VEI-8 event, volcanic explosivity index. It releases more than 1,000 cubic kilometers of material. Such an event would plunge the globe into decades of volcanic winter, blocking the sun with a stratospheric veil of sulfuric acid. In such a scenario, the complex, just-in-time supply chains that keep 8 billion people alive would vanish in a matter of months. Modern agriculture is a machine that runs on sunlight. Take away the sun, and the foundation collapses. A self-sustaining colony on Mars, powered by nuclear or geothermal energy and growing food in pressurized hydroponic labs, would be unaffected by Earth's volcanic winter. It would be the seed vault of human civilization, capable of reseeding the Earth once the skies cleared. Even our sun, the giver of life and the anchor of our existence, is a ticking clock. On a grander, more terrifying timescale, it will one day exhaust its hydrogen, expand into a red giant, and engulf our world in fire. While that event is roughly 5 billion years away, the gradual warming of the sun will make Earth uninhabitable long before it is physically consumed. As the sun ages, its luminosity increases by about 10% every billion years. Within the next 600 million to 1 billion years, the Goldilocks zone, the habitable region where liquid water can exist, will shift outward. The Earth's oceans will evaporate, and the carbon cycle will cease, placing all our eggs in one basket. A single planet is an existential gamble we may not be able to afford. Spreading humanity across multiple celestial bodies is the ultimate insurance policy. It is the act of backing up the hard drive of human culture, art, science, and DNA by establishing self-sustaining outposts on the Moon, Mars, and the moons of Jupiter. We ensure that no single catastrophe, be it a rogue asteroid, a biological plague, or a nuclear tragedy, can erase the story of humanity from the universe. Imagine a future where the human network spans the solar system, the moon, a center for heavy industry, mining, and telescope arrays that peer into the deep past of the universe, Mars, a second hearth, a world of researchers, terraformers, and a new civilization with its own unique culture, the asteroid belt, the economic engine, providing the raw materials for a post-scarcity society. The Jovian moons, outposts like Europa and Callisto, serving as the gateways to the outer solar system. In this model, humanity is no longer a fragile singularity. We become a resilient network. If one node in the network fails, the others endure. The Library of Alexandria was lost because it existed in only one place. The library of human knowledge must not suffer the same fate. We are moving from a species that is stuck on a planet to a species that uses planets to safeguard its future. The transition from survival to prosperity begins with the realization that space is not a void of nothingness, but a treasury of unimaginable wealth. If the previous chapters addressed the why of survival, the moral and existential imperative to move, Chapter 5 is about the how of sustainability. We cannot be a species of explorers if we are constantly tethered to the Earth for every kilogram of oxygen and every bolt of steel. The colonization of the solar system must eventually pay for itself, and the math suggests that it will do so 1,000 times over. Historically, frontiers have always been opened by a combination of higher risk exploration and higher reward extraction. The Silk Road, the Age of Discovery, and the California Gold Rush were driven by the search for resources that were rare in the old world, but abundant in the new. Space is the ultimate iteration of this cycle. The resources of Earth are a tiny fraction of the solar system's mass. We have been living off the scraps of a cosmic table, unaware that the feast is just a few hundred miles above our heads. Imagine a future where the heavy scars of mining are no longer etched into the mountains of Earth, but are instead confined to the dead, airless rocks of the asteroid belt. Near-Earth asteroids and NEAs are rich in platinum group metals palladium, and rhodium, which are essential for the green energy transition on Earth. These materials are the backbone of fuel cells, high-capacity batteries, and the advanced electronics required for a carbon-neutral future on Earth. These metals are rare because they are siderophilic iron-loving. As the Earth formed, most of its platinum sank into the molten core, out of our reach. In asteroids, these metals are distributed throughout the rock. Harvesting a single 500-meter-wide asteroid could yield more platinum than has been mined in all of human history. The economic implications are staggering. We are moving from an economy of scarcity, where we fight over dwindling veins of ore, to an economy of abundance. The first trillionaire will not be a software mogul or a real estate tycoon, but the person who successfully captures and mines a metallic asteroid like 16 Psyche. When the supply of rare metals becomes nearly infinite, the cost of technology plummets, enabling a global standard of living on Earth that is currently unimaginable. Furthermore, the Moon represents a strategic seventh continent. Its proximity makes it the perfect industrial hub, a natural staging ground for the rest of the solar system. The most expensive part of space travel is the gravity tax. It's the energy required to climb out of Earth's deep gravity well. With 1/6 the gravity of Earth and no atmosphere to create drag, launching ships from the lunar surface is exponentially cheaper. This makes the Moon our primary shipyard. In the coming century, we will build the great vessels of the next age in lunar orbit or on the surface of the Mare Tranquillitatis. These ships will be too large, too heavy, and too fragile to ever take off from or land on Earth. They will be true spacecraft, designed in the vacuum, for the vacuum. Using lunar regolith, we can manufacture glass, ceramics, and solar panels. The Moon becomes the foundry of the solar system. We are talking about an industrial revolution that doesn't just change a country, but changes the trajectory of the human race. By moving manufacturing to the Moon, we preserve the Earth's biosphere from industrial pollution, while creating a manufacturing base that can support millions of people living off-world. This economic expansion isn't just about metals and fuels. It's about the democratization of the sky. In the 1960s, space launch was a national event involving thousands of government employees and billions of tax dollars. Today, that monopoly is shattered as the infrastructure of the cislunar economy grows. The space between Earth and the Moon, the cost of entry drops. What was once the sole province of superpowers is becoming the playground of startups, universities, and eventually families. We are building the railroads of the 21st century, but instead of steel tracks across the prairie, we are building cycler orbits between Earth and Mars. An Aldrin cycler is a trajectory that allows a massive station to swing perpetually between Earth and Mars. It's using gravity as its engine. Smaller taxis meet the cycler at each end. This creates a permanent bridge across the stars, a reliable, scheduled transport system that turns a terrifying journey into a routine commute. When space travel becomes a utility, rather than an event, the colonization of the solar system will be unstoppable. The shift to a space-based economy also demands a new understanding of labor and value. In the vacuum, the most valuable commodity is not gold, but human time and biological life. Traditional capitalism relies on the idea that land is the primary asset. In space, habitable volume is the asset. Every cubic meter of breathable air must be manufactured and maintained. This will lead to the rise of infrastructure cooperatives, where the residents of an asteroid base or a lunar city are the shareholders of the very air they breathe. The economic engine of the void will not just create wealth, it will create new forms of governance that prioritize the maintenance of the life support. It's the system above all else. By the time we are mining the moons of Saturn for volatiles and the belt for metals, the Earth-centric economy will be a historical footnote. We will have become a civilization that thrives on the energy of the sun and the raw material of the stars. When we speak of colonization, we often focus on the hardware, the titanium hulls of the rockets, the pressurized domes of the habitats, and the scrubbing cycles of the life support systems. But the most profound changes will be found in the software of humanity. Every time humans have pushed into a new frontier, they have returned with more than just gold, spices, or land. They have returned with new ways of thinking. The harsh, unforgiving realities of space will demand a level of social cooperation and technical ingenuity that our current world, fractured by petty tribalism and short-term thinking, can scarcely imagine. On Earth, we have the luxury of apathy. We can ignore the source of our energy and the destination of our trash because the planet is vast enough to hide our mistakes. In a lunar base or a Martian outpost, apathy is a lethal trait. This environmental intimacy will forge a new kind of human consciousness. The vertical frontier acts as a filter, stripping away the excesses of consumerism and replacing them with a culture of radical pragmatism. This is the birth of the spacer identity, a psychological shift. It values the integrity of the system over the desires of the individual. In a Martian colony, the concept of waste disappears entirely. It is not merely recycled. It is reimagined as a vital resource. When your oxygen is a manufactured commodity, synthesized through the Sabatier process or extracted from regolith, you do not take a breath for granted. When your water is recycled with 99% efficiency, reclaiming every drop of sweat, every exhaled vapor, and every ounce of liquid waste, you develop a profound, visceral respect for the environment. The spacer culture that will emerge on the Moon and Mars will likely be the most environmentally conscious society in history. They will have to be. For a Martian, the environment is not something out there to be visited on weekends. It is the very fabric of their survival. They will live inside the lungs of their machines. This necessity will produce a generation of citizens who understand the delicate balance of an ecosystem better than any terrestrial ecologist. These lessons in extreme conservation will be the greatest export back to Earth. The patents for ultra-efficient closed-loop water systems, the breakthroughs in zero-waste manufacturing, and the blueprints for high-density, low-impact living will flow back to our homeworld. The technology that keeps a colony alive in the sterile dust of Mars will provide the tools to heal the parched soils and polluted oceans of Earth. In our quest to survive the vacuum, we will learn the secrets of thriving on a garden world. Moreover, the scientific bounty of the solar system is a siren call for our curiosity that transcends mere economics. We are a species of storytellers, and we are currently living in a story with only one character. In the ice-covered oceans of Europa and Enceladus, we may find the answer to the greatest question of all. Are we alone? These moons are not just frozen rocks. They are water worlds, with more liquid water than all of Earth's oceans combined. It's kept warm by the tidal kneading of Jupiter and Saturn's immense gravity. To find even a single-celled organism, a cosmic microbe on another world, would be a second Copernican revolution. The first revolution took us out of the center of the universe. The second would take us out of the center of biology. Finding life elsewhere would tell us that the spark is not a fluke of the Earth, but a fundamental property of the universe. It would suggest that the cosmos is not a cold, dead clockwork mechanism, but a fertile field waiting to bloom. Colonizing these worlds isn't just about finding a place to live. It's about finding out who we are and where we fit in the grand cosmic tapestry. This discovery would humble us, potentially ending our terrestrial conflicts by providing the ultimate out-group comparison. As we push outward, we also face a profound ethical horizon. If we find microbial life on Mars or Europa, do we have the right to colonize those worlds? This introduces the concept of planetary protection. Our software must evolve to include a galactic ethics code. We must decide if we are to be conquerors who overwrite existing biologies, or stewards who protect them. The spacer will have to navigate the tension between the primal impulse to expand and the ethical impulse to preserve. This moral complexity will sharpen our collective intellect. We will be forced to define what we mean by life and value in a way that we never had to do while we were confined to a single planet. Finally, The software change will manifest in our politics. Life in space requires a level of radical interdependence. On Earth, you can disagree with your neighbor and never speak to them again. On a space station, that neighbor might be the person responsible for the seals on your airlock. This reality necessitates a shift from conflict-based governance to mission-based governance. Political structures of the Moon and Mars will likely be more decentralized and meritocratic than those on Earth. They will be engineers' republics, where the primary goal of the state is the maintenance of the life support infrastructure. This will lead to a new form of citizenship where every individual has a clear, measurable role in the survival of the collective. The rugged individualism of the American West will be tempered by the total cooperation of the submarine crew. In the end, we go to space not to escape our humanity, but to refine it. The vertical frontier is a mirror. When we look into the blackness of the void, we see ourselves more clearly. We see our fragility, our ingenuity, and our potential. By becoming a multi-planetary species, we are not just expanding our territory. We are expanding our souls beyond the primal instinct for survival. There lie immense, almost incomprehensible opportunities for prosperity. For too long, we have viewed the solar system as a barren wasteland, cold, silent, an empty expanse of vacuum and rock that serves only as a backdrop for the drama of Earth. But this is a fundamental failure of perspective. We have looked at the night sky through the eyes of a desert traveler who sees only sand, unaware that beneath the dunes lies an ocean of oil. In reality, the solar system is an unimaginably rich storehouse of resources, a celestial vault waiting for the right key. Our current economic models are built on the goldsmith's logic. Of the Middle Ages, the idea that value is derived from the extreme rarity of physical matter. We on Earth struggle with the geopolitics of scarcity, engaging in trade wars and physical conflicts over the last accessible veins of copper, as the remaining pockets of lithium, or the control of rare earth elements. We are like children fighting over a handful of crumbs in a room full of unbaked bread. The heavens above us are teeming with the very materials we lack. They are not absent, they are merely elsewhere. Asteroids, the leftovers of the solar system's formation, harbor trillions of dollars worth of precious metals and minerals. These are the fragments of protoplanets that never fully coalesced, pure, unadulterated building blocks of the planetary world. Because asteroids never underwent the process of differentiation, where gravity pulls heavy metals to a molten core, their wealth is not buried thousands of miles deep. It is distributed throughout their surface and interior, accessible to any robotic drill or microwave harvester. A single kilometer wide M-type metallic asteroid can contain more platinum gold, an iridium than has been mined in the entirety of human history. To the modern economist, this sounds like a threat to the market, a deflationary shock that would crash the price of gold. But to the futurist, this is the greatest liberation in history. These are not just shiny trinkets for jewelry. They are the fundamental building blocks of a high-technology future. The true value of space mining lies in its ability to save the Earth from its own industrial appetites. Platinum group metals, PGMs, are the silent heroes of the modern world. They are the essential catalysts for the green revolution, required for the hydrogen fuel cells that provide clean power, the high-capacity batteries for electric vehicles, and the advanced electronics that manage our global power grids on Earth. Extracting these metals requires the movement of millions of tons of earth, the use of toxic chemicals, and the destruction of local ecosystems. In space, mining is an environmentally neutral act. There is no groundwater to poison on a rock like 16 Psyche. There is no atmosphere to pollute in the belt. By tapping into these reserves, which far exceed Earth's dwindling supplies, we move from a linear economy of extraction and waste to a cosmic economy of near-infinite abundance. We shift from a species that mines the cradle to a species that harvests the garden. In this new paradigm, we are no longer limited by what we can dig out of the ground. We are limited only by the reach of our robotics. The economics of space mining will be driven by autonomous system swarms of small, von Neumann-style machines that can identify, latch onto, and process asteroid material without human intervention. These robots will use optical mining, using concentrated sunlight to excavate and turn asteroid water and volatiles into propellant. This creates a self-sustaining industry where the asteroid itself provides the fuel to move its cargo to market. As these technologies mature, the cost of raw materials in the solar system will plummet. We will build orbital habitats not of thin, fragile plastics, but of thick, radiation-shielding steel harvested from the void. We will build solar arrays the size of cities using aluminum, refined in zero-gravity foundries. The transition to this wealth state requires a logistical bridge. Cislunar space the region between Earth and the Moon. This area will become the Suez Canal of the 21st century. It is the transit hub where asteroid resources are processed, neither sent down to Earth or used to build more infrastructure in the black. The Moon plays a vital role here as the refining station, because its gravity is low. It is far more efficient to land asteroid or on the Moon for processing than to bring it into Earth's atmosphere. The Moon's lack of an atmosphere also allows for the use of mass drivers, electromagnetic catapults to launch refined materials back into orbit at a fraction of the cost of a traditional rocket. This expansion will eventually lead to the democratization of wealth. When the scarcity of physical materials is solved, human value will shift from the possession of resources to the application of creativity and knowledge. A cosmic economy is one where the third world of Earth can leapfrog industrial poverty because the raw materials for their infrastructure are being beamed down from above at a cost lower than that of terrestrial mining. Are standing at the end of the age of scarcity. The colonization of the solar system is the door to the age of abundance. By reaching for the stars, we are not just seeking adventure. We are seeking the end of the economic pressures that have driven human conflict for 10,000 years. We are moving from the nursery to the estate. And the inheritance is beyond anything we have ever imagined. The Moon, our closest neighbor, is far more than a poetic light in the night sky. It is a strategic energy depot that holds the key to Earth's ecological salvation. For decades, we looked at the Moon as a barren trophy of a Cold War race. But modern spectroscopy has revealed a prize of staggering potential hidden within its regolith. This fine, gray dust, pulverized by eons of micrometeorite impacts, contains a treasure deposited by the solar wind over billions of years, helium-3, on Earth. Helium-3 is an extreme rarity, shielded from us by our protective atmosphere and magnetic field. On the Moon, which lacks these shields, the isotope has been absorbed into the soil like a cosmic sponge. This is not just another mineral. It is a potential fuel for clean nuclear fusion power, the holy grail of physics. Unlike the nuclear fission reactors of today, which split heavy atoms and produce long-lived radioactive waste. Helium-3, fusion-3, He plus D resulting for He plus P, involves fusing light atoms. The result is a near-limitless supply of energy with virtually no radioactive byproduct and no threat of a meltdown. The energy density is mind-boggling. A few shuttle loads of helium-3, roughly 25 tons, could power the entire United States for a year. The Moon, once a symbol of the unattainable and the dead, may become the very battery that keeps the Earth green, providing the baseload power necessary to finally retire the coal plants and gas turbines that have choked our atmosphere for 2 centuries. Further afield, the red planet beckons with a different kind of treasure, one that is less about wealth and more about will. Water. While the Moon offers energy, Mars offers the chemistry of life. We once thought of Mars as a desiccated desert, but we now know it has vast reserves of water ice, locked away in its polar caps and buried in massive subterranean glaciers beneath its rust-colored soil. In the brutal architecture of space travel, Water is more than just a drink. It is the fundamental currency of the void. Through electrolysis, we can split Martian ice, H2O, into oxygen for breathing and hydrogen for rocket propellant. This is the cornerstone of insight to resource utilization, ESRU. By harvesting Martian water, we solve the tyranny of the rocket equation, the mathematical law that states you must carry fuel to lift fuel, leading to exponentially larger and more expensive rockets. With access to Martian ice, we no longer have to carry every liter of fuel from the deep gravity well of Earth. Mars becomes a refueling station, a gateway to the outer planets like Europa and Titan, and a viable home for a new branch of the human family tree. A rocket arriving from Earth can land, deploy robotic miners to harvest ice, process it into methane and oxygen, and take off again using the planet's own resources. This turns Mars from a one-way destination into a transportation hub. Accessing these resources will do more than fuel a new space economy. It will initiate the great industrial relocation. For 250 years, humanity has engaged in the dirty work of industrializations, melting, and mass manufacturing within the very biosphere we require for survival. We have treated our lungs as the filtration system for our factories. The colonization of the Moon and Mars allows us to shift this industrial footprint into the airless void, where it can do no harm. There are no forests to clear on the Moon, no oceans to pollute on an asteroid, and no endangered species to displace in the Martian craters. We can move our heavy civilization, the parts that produce heat, chemical waste, and carbon off world. In this vision, Earth becomes a residential zone, a planetary park dedicated to biology, art, and the human spirit, while the engine room of our species is moved to the high ground. We are not leaving Earth because we have ruined it. We are moving our factories to the stars so that we can save the Earth by treating the Moon and Mars as the 7th and 8th continents. We begin to see a trade network emerge. The lunar terrestrial route, helium-3 and manufactured zero-G pharmaceuticals flowing down to Earth, high-end consumer goods, and specialized biologicals flowing up the Martian belt. Route, water, and food from Martian greenhouses flowing to the miners in the asteroid belt. Raw metals and minerals flowing back to the Martian shipyards. This is the birth of the cislunar and interplanetary middle class. It is an economy built not on the manipulation of digital bits, but on the mastery of physical atoms. It is a return to a frontier economy where value is created by those who can build, refine, and sustain life in the face of the vacuum. The selection pressure of the vacuum, the very act of colonizing space, demands a level of unprecedented innovation that will ripple through every aspect of human life. We are not just building better rockets. We are pushing the absolute boundaries of engineering, materials, science, robotics, and life support systems. In the terrestrial world, our engineering is often governed by the logic of the good enough. If a car engine fails, you pull over to the shoulder. If a power grid flickering, you wait for the repair crew. However, when you live in an environment where a single leak in a pressure hull, a failed oxygen sensor, or a microfracture in a water recycler means certain death, your engineering must be flawless. There is no shoulder to pull over to halfway between Earth and Mars. This pursuit of perfection creates a technological spillover that is impossible to replicate in the comfort of a terrestrial lab. Space is the ultimate high-stakes auditor. It identifies every flaw in our logic and every weakness in our materials. To survive it, we must transcend our current limits. The legacy of the lunar sprint, we have seen this before. The Apollo missions gave us more than moon rocks and grainy television footage. They provided the foundational architecture of the modern digital age. The need to fit a guidance computer into a cramped command module forced the miniaturization of electronics, directly accelerating the development of the integrated circuit. Without the moonshot, smartphone in your pocket, and the global internet might have been delayed by decades. Beyond electronics, the Apollo effect gave us modern water purification, originally developed to recycle water for astronauts. Breakthroughs in medical imaging like the CT scan, and the cordless tools that revolutionized construction. The colonization of the solar system will be Apollo on a 1,000-fold scale. It is not a temporary sprint, but a permanent expansion that requires a total reimagining of how we interact with matter and energy. The technologies developed for off-world settlements will undoubtedly find applications back on Earth, sparking new industries and improving lives in unforeseen ways. One of the most critical sectors is controlled environment agriculture (CEA), the modular, high-efficiency farming. Techniques required to grow food in a Martian lava tube where every photon of light and every milliliter of nutrient-rich water must be accounted for will revolutionize urban farming in our crowded cities. On Mars, waste is a luxury that doesn't exist. By developing hydroponic and aeroponic systems that can produce massive caloric yields in tiny footprints with zero pesticide use, we provide the blueprints for feeding a terrestrial population of 10 billion on a shrinking amount of arable land. We are learning how to turn the hostile into the habitable, a skill that will be essential as climate change shifts Earth's own agricultural zones. The quest for the stars also forces a revolution in how we build. The ultralight, radiation shielding materials designed for deep space transit must be capable of blocking high-energy cosmic rays while remaining light enough to launch. These materials, carbon nanotubes, graphene composites, and aerogels will lead to more efficient buildings and safer transportation on the ground. Imagine skyscrapers built from materials stronger than steel, but light as air. Or electric vehicles that are virtually indestructible thanks to self-healing polymers developed for spacecraft hulls. The shielding we develop for the Martian surface will become the skin of our terrestrial infrastructure, making it more resilient to the extreme weather events of a changing climate. Robotics will undergo a transformation even more profound. To mine an asteroid or build a robotic lunar base before the humans even arrive, we need machines that can operate with a level of autonomy, dexterity, and common sense far beyond what we currently possess. These are not the tethered robots of a factory floor. These are autonomous exploration units that must navigate 3D terrain, make split-second repair decisions, and manage complex chemical refineries. Without a human pilot in the loop, these advancements in robotics and artificial intelligence will flow back to Earth, automating the most dangerous jobs in mining, undersea exploration, and disaster response. They will assist in complex surgeries where sub-millimeter precision is required and manage the intricate, real-time logistics of a globalized world. When an AI can successfully manage the life support system of a Mars colony, balancing oxygen, heat, pressure, and energy for years at a time, managing a terrestrial smart city becomes a trivial task. The quest for the stars is, in reality, quest for a better life on Earth. We do not choose between solving problems at home and exploring the void. Rather, the one fuels the other. Space is the grand challenge that forces us to solve Earth's problems faster. It provides the pressure that turns the coal of our curiosity into the diamond of our innovation. In the 21st century, the measure of a nation's and species vitality will be its contribution. To this high-technology frontier, we're not just going to space. To find a plan B, we're going to space to upgrade plan A. By pushing our limits in the stars, we ensure that we never reach our limits on Earth, beyond the hardware and the minerals. There is the profound psychological impact of the frontier. History shows us that periods of exploration are also periods of intense intellectual and cultural growth. The Renaissance was not merely a result of internal European stability. It was fueled by the psychological shock of the New World, the realization that the maps were wrong. The ancients were incomplete, and the horizon was wider than the church or the state. I never whispered, when we are forced to solve the problems of living in space, we are forced to reevaluate how we live on Earth. The vacuum does not allow for the luxury of dogma. On the frontier, reality is the ultimate arbiter. This frontier empiricism will bleed back into human culture, sparking a second enlightenment where evidence-based thinking and long-term planning replace the reactive, emotion-driven politics of our current era. The extreme cooperation required to maintain a lunar colony or a Martian settlement will provide new models for governance and conflict resolution. On Earth, our political systems are designed to manage conflict between competing groups. We have the luxury of zero-sum games because if one group loses, the biosphere still sustains them. In a space colony, this logic is suicidal. In a place where everyone breathes the same recycled air, us versus them mentalities become a lethal liability. If a disgruntled faction sabotages the oxygen scrubbers to spite their rivals, everyone dies. There is no other side of the airlock. This creates a biological social contract, a realization that the individual's survival is 100% dependent on the integrity of the collective's life support system. This radical interdependence will forge a new form of spacer citizenship, where cooperation is not a moral choice, but a survival instinct. The colonization of the solar system will be the ultimate unifier. Historically, humanity has only found unity when faced with a common enemy or a common goal. Thus far, we have largely relied on enemies. Space travel offers the common goal. It gives humanity a common purpose that transcends national borders, religious divisions, and ancient grievances. When we look back at the Earth from the distance of Mars, the borders that we have bled over for centuries disappear. The Great Walls and the Iron Curtains are invisible. All that remains is a pale blue dot, a fragile, shared home that requires a unified defense and a unified future. This overview effect, once the exclusive privilege of a handful of astronauts, will become the foundational perspective of the human race. It turns our gaze outward, away from the small patches of dirt we fight over, and toward the vast, shared heritage of the cosmos. The modern world is plagued by short-termism. Our corporations think in fiscal quarters. Our politicians think in election cycles. This temporal myopia makes us incapable of addressing long-term threats, like climate change or resource depletion. The colonization of space is a project that will take centuries. You cannot terraform a planet in a 4-year term. You cannot build a Dyson swarm in a decade. This undertaking provides a sense of continuity and long-term thinking that is sorely lacking in our modern culture. It requires us to build cathedrals in the black projects started by one generation, managed by another, and completed by a third. By committing to the stars, we are teaching ourselves to think in deep time again. We are moving from the frantic, desperate pace of a species in crisis to the measured, confident stride of a species with a future. As these outposts grow, we will see the emergence of a unique cislunar and Martian culture. This will not be a mere copy of Earth's cultures. It will be a synthesis. In a colony made up of the best scientists and engineers from every nation on Earth, a new Creole of the stars will emerge. Language, a blend of technical jargon and multilingual slang. Art, sculptures designed for 1/6 gravity. Music that utilizes the resonant frequencies of pressurized hulls. Philosophy, a worldview that prioritizes the stewardship of the artificial, the understanding. that we are the creators and maintainers of our own world. This cultural evolution is the final step in our journey. We are not just moving our bodies to other planets. We are evolving our minds to be worthy of the universe. The software of humanity is being rewritten to be more resilient, more cooperative, and more curious. Finally, beyond the cold, binary calculations of resource acquisition and the dire, mathematically sound warnings of existential risk. There exists the most powerful driver of all, the innate human drive to explore, to understand, and to push the boundaries of what is possible. This is not a matter of spreadsheets, orbital mechanics, or survival strategies. It is a matter of the soul. We are the only creatures on this planet that ask why, and what lies beyond. This restlessness is not a bug in our programming. It is the core of our operating system. It is the same restless spirit that led our ancestors to chart unknown and terrifying seas in wooden hulls with nothing but the stars for guidance. It is the same impulse that drove us to climb the highest, most oxygen-depleted mountains where the air is thin and the cold is absolute, and to trek across frozen wastes where no life was meant to survive. We are at our core a species of the frontier. To stop exploring is to stop being human. A humanity that is no longer pushing its boundaries is a humanity that has begun the slow, agonizing process of cultural and intellectual decay. Stagnation is the precursor to extinction. A species that ceases to grow inevitably begins to shrink. Space colonization represents the ultimate challenge test of our collective will, our intelligence, and our courage. It is the great filter of our era. Unlike the frontiers of the past, which were often defined by horizontal conquest, the zero-sum game of taking land from others, the vertical frontier of space offers a unique opportunity to unite humanity. In the void, there is no land to steal, only environments to build. The enemy is not another tribe. The enemy is the vacuum, the radiation, and the distance. The sheer scale of the endeavor, the engineering required to bridge the vacuum. The biology required to sustain life in the void transcends the capabilities of any single nation or corporation. No single flag is large enough to cover the Martian landscape. It is a common, awe-inspiring endeavor that demands a global we. When the first footprints are pressed into the red dust of Mars, they will not belong to a country, a party, or a titan of industry. They will belong to a species. This journey demands a shift in our political and social architecture. It requires a mission-oriented civilization. For the first time, we have a project that is too big for our ancient grievances. The complexity of a Martian transit vehicle or a lunar smelting plant forces a radical level of transparency and cooperation. You cannot build a multi-planetary bridge on a foundation of secrets and silos. In this sense, space is the catalyst for the unification of Earth. We often speak of the Earth as our home, but the more accurate term is cradle. Cradle is essential, providing warmth, protection, and the nutrients required for early growth. But a child who never leaves the cradle never truly fulfills their potential. Our journey into the solar system is the great maturity of the human race. By establishing self-sustaining cities on Mars, hollowed-out asteroid colonies in the belt, and orbital habitats at the Lagrange points, we are finally outgrowing the cradle. We are moving from a fragile singularity of species that could be ended by one bad day in the asteroid belt to a resilient multi-planetary network. This is the moment humanity moves from being a biological accident on a lucky planet to becoming architects of the cosmos. This journey offers a future where humanity is not confined to a single world. Imagine a child born in the 22nd century. To them, humanity isn't just the people on Earth. It's the miners on Ceres, the researchers in the cloud cities of Venus, the farmers in the Martian lava tubes, and the engineers on the Jovian moon arrays. This child will grow up with a perspective that is truly solar. It will see the solar system not as a series of distant lights, but as a neighborhood. We are taking our first tentative steps into the vast nursery of the stars. The colonization of the solar system is just the beginning, the foundation era. Beyond our sun lie billions of other stars, many with their own planets, their own resources, and perhaps their own mysteries. By mastering our own backyard, we are developing the spacefaring muscle required to eventually cross the interstellar gulf. In the final analysis, our expansion into space is an act of faith in ourselves. It is a declaration that the human story is worth telling, and that it should never have a final chapter. We are the torchbearers of consciousness in a universe that is largely silent. By spreading that flame to other worlds, we ensure that the light of reason, art, and love continues to burn for as long as there are stars in the sky. We stand at the precipice. Behind us is the long, violent, and beautiful history of our planetary childhood. Ahead of us is the infinite potential of our cosmic adulthood. The door to the universe is open. All we have to do is find the courage to walk through it. Becoming a multi-planetary species is about more than just physical presence on other worlds. It is about the fundamental expansion of human consciousness. For all of recorded history, our identity has been tied to the terrestrial. We've been defined by the horizon, the 24-hour cycle of light and dark, and the crushing but comforting embrace of 1 gram of gravity. Our languages are saturated with earthbound metaphors. We ground ourselves. We land on ideas. We speak of the world as a synonym for existence. Our religions, our philosophies, and our social structures are all rooted in the seasons and the biological rhythms of Earth. But as we establish permanent settlements on the Moon, Mars, and the asteroids, this umbilical cord will begin to fray. A new identity will emerge. We will cease to be a worldly species and become citizens of the solar system. This is not merely a change in address. It is a change in the self. Imagine a generation of children for whom the world is not a single blue marble, but a sprawling, vibrant network of habitats stretching from the sun-scorched orbit of Mercury to the frozen, methane-shrouded moons of Saturn. For these children, the sky is not a ceiling, but a highway. They will grow up with the understanding that humanity is a distributed intelligence. This shift in perspective will foster an unprecedented era of innovation. On Earth, we are often held back by the path dependency of our existing infrastructure. It is hard to build a new city when an old one already stands in its place. But in the void, every habitat is a blank slate. We will be forced to solve problems that simply do not exist on Earth. How to build vertical cities in the low gravity of the Moon. How to farm with artificial light filtered through Martian dust, and how to create stable, democratic societies in isolated environments where the air you breathe is a communal product. These challenges will act as a pressure cooker for human genius. When survival depends on innovation, progress is not a choice. It is a mandate. We will see the birth of solar architectures and low-G athletics, and perhaps even new forms of biological adaptation. This relentless need to problem solve will accelerate our progress in materials, science, and biotechnology in ways we cannot yet imagine. But more importantly, this expansion ensures our long-term survival through a process of existential diversification. By diversifying our habitats, we move from a single point of failure model to a resilient, decentralized network, in the language of the information age. If Earth is the server of humanity's the primary storage site for our DNA, our history and our culture, then the colonies are the off-site backups. We live in a universe where information is fragile, Civilizations can be silenced by a single asteroid, a solar flare, or a self-inflicted biological error. By spreading our archives to the lunar lava tubes and the Martian archives, we ensure that our music, our science, and our memories are never lost to the silence of the void, even if the home server faces a catastrophic crash. The human story continues. The symphonies of Beethoven, the equations of Maxwell, and the collective history of our struggles will be mirrored across the solar system. We are essentially uploading humanity into the stars, making us a redundant and therefore immortal species. As the distance between Earth and its colonies grows, the solar citizen will develop a new set of values. They will prioritize sustainability because they live in closed loops. They will prioritize cooperation because the vacuum is an indifferent enemy. They will prioritize long-termism because they are building worlds that will take centuries to mature. This new identity will eventually flow back to Earth, influencing those who remained on the home planet. The solar perspective will teach the terrestrial population that we are all on a spacecraft Earth and that our resources must be managed with the same precision and care as a Martian oxygen recycler. We stand now at the most significant crossroads in the history of life. We are the first generation with the technology to leave the cradle, and the first generation with the data to know why we must. The transition from a planetary species to a multi-planetary one is the biological equivalent of the move from the sea to the land, a leap that changes the definition of what it means to be alive. The journey is long. The risks are immense, and the costs are staggering. But the cost of staying is the eventual silence of our species. We go to the moon, to Mars, and to the stars beyond, not because it is an easy escape, but because it is our destiny to be the eyes and ears of the universe. We are finally outgrowing the cradle and taking our first steps into the vast nursery of the stars. The human story is just beginning. At its heart, the colonization of the solar system is about inspiration. It is about providing future generations with a vision that is grander than the mundane, often paralyzing problems of the present. In an age often characterized by a pervasive cynicism, sense that we have reached the end of history and that our only future is one of managed decline and resource wars, the space frontier offers a radical narrative of beginning. For the first time in centuries, we are not looking at our world as a shrinking island of dwindling possibilities, but as a launching pad. Space is the grandest adventure imaginable, a story where we are no longer merely the passive observers of a cold and different cosmos, but active, conscious participants in its unfolding. This shift from observer to participant is the most significant psychological upgrade in the history of our species. It moves us from a state of planetary anxiety to a state of cosmic agency. By securing our place in the cosmos, we fulfill a destiny that began the moment. A primitive human first pointed at a wandering planet in the night sky and wondered if it was a god, a world, or a dream. That curiosity was the first step on a ladder that leads to the stars. We are moving from being mere inhabitants of Earth passengers on a biological ship we didn't build to becoming the stewards of our solar neighborhood. This is the transition from survival to stewardship. We establish ourselves on the moon, Mars, and the Jovian moons. We take on the responsibility of managing environments. We learn to balance atmospheres, to shield life from radiation, and to create ecosystems where none existed. This mastery of the physical world is the ultimate maturation of the human intellect. This transition will inspire a new renaissance in art, literature, and science. History teaches us that whenever the physical horizon expands, the creative horizon follows. The New World gave us the height of European cartography and the rise of the modern novel. The high frontier will give us art forms we cannot yet name. We will find new ways to describe the beauty of a Martian sunset, where the sky turns blue as the sun sinks into a pink horizon, or the majesty of Saturn's rings seen from the surface of Enceladus, where the ice fountains spray into the blackness of space. Our poets will speak of the earthlight that illuminates the lunar night, and our scientists will write the laws of a physics that operates in the deep wells of the outer giants. This explosion of culture will revitalize the human spirit, providing a sense of meaning that is often lost in the noise of a digital terrestrial existence. We are not just escaping a fragile cradle. We are finally claiming our inheritance. The solar system is not a wasteland to be plundered, but an estate to be managed. It is an environment rich with the energy of a middle-aged star and the raw materials of 1,000 worlds. By reaching out, we are becoming more than we were. We are shedding the limitations of a single planet, species, and adopting the resilience of a multi-planetary one. We are reaching for a future where the light of human reason and compassion, the very best of what we are, shines across the dark reaches of space. This is the ultimate insurance policy for the soul. It ensures that our story, the story of our music, our art, our love, and our struggle is not a brief, it's a tragic flicker in the night of time. Instead, it becomes a steady, enduring flame that lights the way for billions of years to come. The journey of 1,000 millennia began with a single step out of the Great Rift Valley. It continues now with the ignition of a rocket engine and the deployment of a solar sail. We are the architects of the bridge between the Earth and the stars. The cradle is behind us. The universe is before us. And for the first time, we are ready to walk through the door as we weave together these disparate threads, the cold necessity of survival, the glittering promise of post-scarcity abundance, and the haunting call of the frontier. We begin to see that the colonization of the solar system is not merely a policy choice or a luxury of the wealthy. It is an inevitability. It is the logical and biological conclusion of the human experiment. We have spent thousands of years mastering the terrestrial. We have dammed the rivers, mapped the genomes, and harnessed the atom. Now, we must learn to master the neighborhood. The why of our journey has never been clearer or more multifaceted. We go to save ourselves from the statistical certainty of planetary catastrophe. We go to enrich ourselves, moving beyond the zero-sum games of a finite Earth into the infinite bounty of the high ground. And, perhaps most importantly, we go to find ourselves to discover what the human spirit is truly capable of when it is stripped of its terrestrial comforts and forced to innovate in the heart of the vacuum, the infrastructure we are laboring to build today, the heavy-lift reusable rockets, the pressurized lunar outposts, the high-bandwidth deep space communication, are more than just pieces of hardware. They are the stones of a bridge. This bridge does not just lead to the dust of Mars or the metallic riches of the asteroid belt. It leads to a future where humanity is no longer a victim of planetary circumstance. For the entirety of our history, we have been at the mercy of the Earth. We have been shaped by its climate, limited by its gravity, and threatened by its geological whims. By building this bridge, we are changing the nature of that relationship. We are transitioning from a species that happens to the universe, a biological accident clinging to a rock, to a species that happens with the universe. We are becoming an intentional force of nature. Every technical breakthrough in life support, every brave pioneer who accepts the solitude of a long-duration mission, and every resource-rich asteroid captured and processed is a step away from the precariousness of a single-world existence. This is the process of cosmic maturation. A planetary species is like a child in a nursery, dependent on its environment for everything. A multi-planetary species is like an adult who has learned to build their own home, grow their own food, and manage their own energy. This transition is arguably the most significant event in the 4 billion-year history of life on Earth. It is the moment life becomes truly independent of its planet of origin. This is the legacy we leave for those who will follow a universe that is no longer a cold, indifferent, and terrifying void, but a home. The pioneers of the 21st century are the founding fathers and mothers of a solar civilization. The challenges they face today, the radiation shielding, the bone density loss, the isolation, are the growing pains of a species destined for the stars. Centuries from now, when human habitats encircle the sun in a vast Dyson swarm, and our probes are entering the atmospheres of exoplanets and distant star systems, our descendants will look back at this era. They will look back at our first tentative steps on the moon and our first rust-dusted colonies on Mars with the same reverence we feel for the first humans who crossed the Bering Land Bridge. They will recognize that we chose the difficult path over the easy one, and in doing so, we ensured that the story of humanity would never end. We are moving toward a future where the light of human reason is not a brief flicker in the night, but a steady flame that lights the way for billions of years to come. The cradle has served us well, but the horizon is calling. We have prepared the ships, we have done the math, and we have felt the impulse. It is time to cross the bridge. Before we venture deeper into the chaotic beauty of the solar system, the moon stands as our nearest and most accessible celestial neighbor. Silver sentinel that has watched over human evolution since its inception. In the grand strategy of space colonization, the moon is not merely a destination or a relic of the Cold War's space race. It is the logical first step, a critical proving ground for the technologies and strategies required for sustained off-world living. Establishing a permanent human presence on the moon isn't just a nostalgic return to the footprints left by the Apollo astronauts. It is the construction of a foundational pier. In the cold math of orbital mechanics, the moon is our harbor. Without the moon, the journey to Mars is a leap across a terrifying chasm, a high-stakes gamble, where every failed component is a death sentence. With the moon, it is a series of manageable, calculated strides. We go to the moon to learn how to live in the black, so that when we go to Mars, we go as veterans, not as victims. The moon offers us something that no simulation on Earth can provide: a real-world environment of extreme vacuum, abrasive lunar dust, and 1/6 gravity. These are the three horsemen of lunar engineering, the primary antagonists that our technology must defeat before we can claim the status of a multi-planetary species. On Earth, we can simulate a vacuum in massive chambers, but we cannot truly replicate the relentless, jagged nature of lunar regolith. Unlike terrestrial sand, which is tumbled by wind and smoothed by water over eons, lunar dust is composed of microscopic shards of volcanic glass and mineral, fragments that have remained razor-sharp for billions of years. This dust is chemically active and physically aggressive. It has never been weathered. These shards chew through industrial gaskets, jam the articulated joints of rovers, and, if inhaled, irritate lungs with the same lethality as weeds, asbestos. By establishing a permanent base at the lunar South Pole specifically, in the peaks of eternal light, we force our materials science to evolve under the most brutal conditions. We learn to create seals that don't leak over years of thermal cycling, bearings that don't seize in the presence of glass dust, and fabrics for spacesuits that don't tear when brushed against a lunar rock. These lessons, bought in the harsh lunar daylight, where temperatures swing from boiling to cryogenic, will be the operating system for every future colony. The lunar base is the beta test for the human future. The 1/6 gravity of the moon. It's perhaps the most intriguing biological variable. We know how the human body decays in zero gravity, as seen on the International Space Station, and we know how it thrives in the one gravity of Earth, but we have no long-term data on the partial gravity middle ground. Will the human heart maintain its strength at 1/6 gravity? Will the vestibular system adapt? Or will future lunar citizens suffer from a permanent sense of disorientation? The moon allows us to answer these questions just 3 days away from the safety of Earth's medical facilities. This makes it the only ethical place to study the physiological changes that will eventually define the Martian 0.38 grams and asteroid 0 grams populations. We are essentially using the moon to debug human biology for the cosmos. The strategic choice of the lunar South Pole, specifically areas like the Shackleton crater, is not accidental. This region offers a unique oasis of physics. On the rims of these craters, the sun almost never sets, providing a near-constant source of solar energy. Just a few kilometers away, in the crater floors that have been in shadow for 2 billion years, lie vast deposits of water ice. This proximity of constant power and raw volatiles is the golden spike of lunar colonization. It allows us to test cryogenic resource extraction, learning how to mine ice at 200 Celsius and turn it into the lifeblood of a colony. If we can master the art of harvesting ice in the dark of a lunar crater, we can harvest it anywhere on the moons of Saturn, in the heart of a comet, or beneath the red sands of Mars. The moon also serves as our first off-world gas station, because the moon has no atmosphere and low gravity. It is the ideal place to store and launch fuel. A kilogram of fuel produced on the moon and launched into low Earth orbit (LEO) requires significantly less energy than a kilogram launched from Earth. This creates a cislunar economy. We move from a lander mindset to a commuter mindset. We build a fleet of reusable tugs that move between Earth orbit and lunar orbit, fueled by lunar water. This infrastructure is the prerequisite for Mars. It turns the journey to the red planet from a special event into a logistical routine. We aren't just building a base. We are building the first node of a solar system-wide transportation network. Finally, the moon provides a psychological bridge. For the first time, humans will look up at the night sky and see the lights of a city looking back at them. It will be the first time that home is not just the ground beneath our feet, but also the light in the sky. This will break the planetary monopoly on human thought. The moon is our training ground, our shipyard, and our library. It is the place where we leave behind the fragility of our childhood and accept the responsibilities of our cosmic adolescence. By the time we leave the moon for the deeper reaches of the solar system, we will have transformed from Terrans into spacers. The primary reason the moon is a stepping stone is not merely poetic or proximity-based. It is purely mathematical. We must contend with the fundamental physical reality of the gravity well. Earth is a massive, dense planet that exerts a powerful gravitational grip on everything within its reach. To escape Earth's atmosphere and enter orbit, a rocket must reach a velocity of approximately 11.2 kilometers per second. This requires an immense amount of energy, which in turn requires an immense amount of fuel. The tyranny of the rocket equation dictates that to carry more fuel, you need a bigger tank, which makes the rocket heavier, which requires more fuel to lift that extra weight. This is why the Saturn V rocket was over 100 meters tall. Just to send a tiny capsule to the moon, every kilogram of fuel, water, or air we want to send to Mars or the asteroid belt must be hauled out of this deep terrestrial well at immense cost. It is like trying to start a cross-country road trip by driving up a vertical cliff. The moon, however, offers a different mathematical reality. It has a much shallower gravity, well about 1/6 that of Earth. Launching a vessel from the Lunar surface requires only a fraction of the energy needed to launch from our home planet. This is the high ground advantage. If we can establish a base of operations there, we aren't just visiting a neighbor, we're moving to a higher energy state in the solar system. This gravitational advantage makes the moon the ideal shipyard for the future of humanity. On Earth, we are limited by the aerodynamic requirements of launching through a thick atmosphere. Ships must be streamlined, rigid, or incapable of withstanding the immense G-forces of a vertical ascent. On the moon, these constraints disappear. We can construct vessels in the vacuum ships that are massive, modular, and designed entirely for the long haul. These vessels never have to touch a planetary surface. It can be spindly, efficient, and optimized for ion or nuclear thermal propulsion. By using lunar-harvested titanium and aluminum, we can build a fleet of true spacecraft that are berthed in the shallow well of the moon, ready to traverse the solar system without ever fighting the friction of an atmosphere. The cornerstone of this shipyard is the ability to harvest lunar water. We now know that water is locked as ice in the permanently shadowed craters of the lunar outpoles, places where the sun hasn't shone for 2 billion years. This ice is more than just a life support resource. It is the oil of the 21st century. Through the process of electrolysis, we can crack that lunar water H2O into its component parts, liquid hydrogen and liquid oxygen. This is the birth of the lunar gas station. This logistics chain fundamentally changes the economics of the solar system. Instead of launching massive, fuel-heavy ships from Earth, we can launch lean, efficient taxis or ferries. These ferries carry the crew and delicate electronics out of Earth's deep well and dock at a Lunar Gateway, a space station in a near rectilinear halo orbit. There, they refuel with propellant manufactured on the lunar surface, taken from the gas station in the Shackleton crater. Only then do they ignite their heavy engines for the long journey to the outer planets. This shift transforms space travel from a series of expensive one-off expeditions into a sustainable, repeatable transport system. It is the transition from the era of the explorer to the era of the resident. The moon is the logistical anchor of the cislunar economy. In this new economic model, the space between the Earth and the moon becomes a busy corridor of commerce and industry. We will see propellant depots, orbital warehouses, where fuel is stored and traded, tug, autonomous robotic craft that move cargo between LEO low Earth orbit and LLO low lunar orbit cycler stations, massive habitats that stay in permanent transit, providing a safe, shielded environment for travelers. By establishing this gas station and shipyard, we effectively decouple human progress from the limitations of Earth's gravity. The moon becomes the front porch of humanity, the place where we gather our tools, fuel our ships, and prepare our minds for the vastness that lies beyond. We are no longer just looking at the stars. We are building the harbor that will take us there. Life on the moon will be a masterclass in closed-loop ecology. On Earth, we have lived for millennia with the illusion of the external, the belief that we can throw things away or draw from limitless wells. The moon shatters this illusion instantly, because the cost of bringing supplies from Earth's deep gravity well is prohibitive. Currently, thousands of dollars per liter of water. Lunar colonists will have to become the most efficient recyclers in the history of our species. In a lunar habitat, the environment is not a backdrop. It is a life support machine. Every breath of CO2 exhaled by a colonist must be mechanically or biologically scrubbed and turned back into. Every drop of wastewater from showers sinks. And even the humidity in the air must be captured and purified to better than pristine standards. Every scrap of organic waste, from food trimmings to human bio-waste, must be processed into the hydroponic and aeroponic beds that grow the colony's nutrient-dense crops. This level of total, uncompromising sustainability is not just a moral choice. It is a biological prerequisite for Mars. On the red planet, the resupply window only opens once every 26 months, when the planets align. If you cannot maintain a closed loop on the moon just 3 days from home, you cannot survive the years of isolation on Mars. The moon is where we learn to live in a state of perfect balance with our environment. These lessons in extreme conservation will be the moon's most valuable export to Earth. The technology required to sustain 20 people in a lunar lava tube, recycling water with 99.9% efficiency, and growing a year's worth of food in a space the size of a shipping container is exactly the technology needed to save Earth's overstressed biosphere. The lunar economy will feed back into the terrestrial economy, providing the blueprints for zero-waste cities, drought-resistant agriculture, and atmospheric carbon capture. By learning to survive in the sterile vacuum of the moon, we will gain the tools to restore the garden of the Earth. But the moon offers more than just survival training. It offers a scientific vantage point unlike any other in the solar system. The moon is tidally locked, meaning one side always faces away from our home planet. This far side of the moon is the most radio-quiet location in the inner solar system. On the far side, shielded from the relentless cacophony of Earth's radio interference, cell phone signals, and television broadcasts by 3,000 kilometers of solid rock, we can build the most sensitive radio telescopes in existence. Free from the noise of civilization and the haze of a thick atmosphere, these arrays can peer back into the dark ages of the universe, the era before the first stars even ignited. We can detect the faint, low-frequency whispers of the earliest cosmos, seeing the very first structures of the universe take shape. We can map the magnetospheres of exoplanets and distant star systems, looking for the telltale signs of habitability around other suns. The moon is not just a stepping stone for our feet. It is a pedestal for our vision. It allows us to look deeper into the cosmic tapestry than we ever could from the hazy, noisy environment of our birth world. In this sense, the moon fulfills the dual nature of human progress. It satisfies the pragmatist, who seeks the technology of survival and the resources of the future. And it satisfies the dreamer, who seeks to understand our place in the infinite. By the time the first permanent lunar cities are established, the moon will have changed us. We will have learned how to be sustainable in the truest sense of the word. And we will have seen further into the past than any generation before us. We go to the moon to learn how to live, but we stay to learn how to see. Finally, beyond the physics of the gravity well and the chemistry of the closed loop, the moon serves as a profound psychological transition. It is the shallow end of the cosmic pool, positioned only 3 days away from Earth, a distance shorter than the time it took the first explorers to cross the Atlantic. The moon offers a unique safety net. In the early decades of colonization, its proximity is the difference between a tragic footnote and a successful learning experience. If something goes wrong, a sudden medical emergency that exceeds the colony's surgical capabilities, a critical hardware failure in the primary oxygen scrubbers, or an unforeseen psychological breakdown, help, or at least a path home, is relatively close. This proximity allows us to take risks that we wouldn't dare take on a 2-year round trip to Mars. On Mars, if a critical system fails, you must fix it or perish. On the moon, you can fail, you can learn, and most importantly, you can iterate. The moon allows us to build a culture of resilient engineering where we can test the limits of our technology without betting the entire species on a single mission. The moon also allows the first spacers to adjust to the crushing reality of the vacuum while maintaining a visual tether to their origins. For a lunar colonist outside is a lethal environment, a silent world of radiation and extreme temperatures. Yet, when they look up through the reinforced glass of a cupola, they see their home planet hanging large, bright, and impossibly blue in the velvet blackness. This Earth view is a powerful psychological stabilizer. It prevents the sense of cosmic loneliness that is expected to plague the first Martian pioneers, for whom Earth will be nothing more than a faint, indistinguishable blue star. The moon allows us to gradually wean ourselves off the planetary surface. It is the place where we learn to live in a world of manufactured air and recycled water, while still being able to see the garden from the window. When we eventually do send the first crew to Mars, they will not go as the wide-eyed explorers of the 1960s. They will go with the cold, quiet confidence of a species that has already mastered the lunar environment. They will not be Earthlings in a foreign land. They will be spacers moving to a new district, the first Martian expedition will use the same habitat modules that have withstood decades of lunar dust. They will rely on the same radiation shielding composites that have protected lunar children from solar flares. And they will drink from the same water recycling systems that have been refined to perfection in the Shackleton crater. The moon is the crucible, where the Earthling is forged into the solar citizen. It is where we shed our terrestrial skin, our dependence on the passive hospitality of nature, and accepts the responsibility of creating our own world. In the lunar lava tubes, we will develop new traditions, new slang, and new ways of perceiving time. We will stop identifying as inhabitants of a country and start identifying as stewards of the light by conquering the moon. We prove to ourselves that we are no longer tethered to a single world. We demonstrate that our intelligence is not a local phenomenon of the Earth, but a universal force capable of thriving in the void. We prove that the cradle was just the beginning and necessary starting point, but not a final destination. The footprints we leave on the moon today are the foundation of the cities we will build on Mars tomorrow. We are no longer a species waiting for the next extinction event. We are a species taking control of its own timeline. The Silver Sentinel has finished its watch. Now, it is time for us to take ours. To complete the final movements of this 10,000-word manuscript, we expand on the economics of proximity and the industrial alchemy of low gravity. This section details how the moon acts as both a protective, training wheels environment for humanity and a high-tech foundry for the next generation of terrestrial and celestial products. The moon's proximity a mere 3-day journey across the translunar coast makes it an ideal location for testing and developing the critical systems that will eventually sustain life in the far reaches of the solar system. In the unforgiving hierarchy of space travel, distance is synonymous with risk. If a primary life support system fails on a transit to Mars, the crew is months, perhaps even years, away from any hope of rescue or resupply. In deep space, time is the one resource you cannot manufacture. However, the moon is close enough to be within our reaction zone. It offers a 3-day safety margin, period short enough to survive on emergency reserves, but long enough to demand that our systems be robust, self-reliant, and capable of autonomous repair. This 3-day bridge allows us to iterate on habitat design, closed-loop life support, and emergency medical protocols with a safety net that no other celestial body can provide. We go to the moon to fail safely so that we can succeed on Mars permanently. It is the only place in the cosmos where we can test the limits of human endurance while keeping the lifeboats within reach. Because of this accessibility, the moon becomes more than a survival camp. It becomes the premier laboratory for what economists are calling the microgravity renaissance. It offers a low-gravity environment 1/6 of Earth's that is perfect for material processing. experiments that are physically impossible on our home planet, on Earth. Gravity is a constant interloper in the manufacturing process. It causes convection, the uneven rising of heat and sedimentation, the settling of heavier particles, both of which interfere with the delicate formation of molecular structures. In the stable, low-gravity environments of lunar labs, we can achieve a level of atomic-level precision that is the dream of every materials scientist. In these lunar foundries, we can manufacture ultra-pure fiber optics, such as Zeppelin, which can transmit data over vast distances with virtually no signal loss. A feat impossible in Earth's gravity, where impurities settle during the cooling process. We can cultivate superior pharmaceuticals, growing large, perfect protein crystals that allow researchers to design more effective drugs for cancer and neurological disorders. We can create exotic metal alloys, blends of elements that refuse to mix on Earth but combine perfectly in the lunar void, resulting in materials that are lighter than plastic but stronger than titanium. These are not merely scientific curiosities. They are high-value exports. A single kilogram of high-purity optical fiber or a specialized lunar-grown protein can be worth more than its weight in gold. These products create a self-sustaining economic loop. The profits from made on the moon. Exports can pay for the very oxygen, water, and infrastructure required by the colony. This shifts the narrative of space colonization from one of expenditure to one of investment. Moon ceases to be a drain on terrestrial taxpayers and becomes a profit-generating hub of the global economy. By leveraging the unique physics of 1/6 gravity, the moon provides the capital, both intellectual and financial, required to fuel our further expansion toward the asteroid belt and beyond. We are using the physics of the neighbor to fund the journey to the stars, beyond industry and survival. The moon offers a stable, vibration-free platform for astronomical observatories, free from Earth's atmospheric interference. For as long as humans have looked at the stars, we have done so through a veil. Our atmosphere, while essential for life, is a chaotic fluid that distorts our vision. Astronomers on Earth must contend with seeing the shimmering of the air caused by temperature fluctuations that blurs the light of distant stars. Even our most advanced adaptive optics are merely a filter, trying to correct for a fundamentally noisy medium. Furthermore, we are increasingly blinding ourselves. The modern astronomer faces the twin plagues of light pollution from sprawling megalopolises and the ever-growing swarm of satellite constellations that streak across long exposure images like digital scars. The moon, by contrast, is the ultimate sanctuary for light. It has no atmosphere to blur the incoming photons and no sky glow to hide the faintest, oldest galaxies in the universe. On the moon, the stars do not twinkle. They burn with a steady, unwavering brilliance. By placing telescopes in the lunar craters, specifically at the poles where temperatures remain constant and cryogenic, we can observe the universe in wavelengths that are normally absorbed or reflected by Earth's ozone layer and water vapor. Much of the universe's story is written in the ultraviolet and infrared spectrums, portions of the light scale that the Earth's atmosphere effectively mutes. Lunar-based observatories can see the invisible universe. We can build gargantuan liquid mirror telescopes spinning vats of reflective fluid in the lunar low gravity that would collapse under their own weight on Earth, because the moon is geologically quiet compared to the Earth. These instruments can maintain a level of sub-millimeter precision for decades. These lunar eyes will allow us to look back to the very dawn of time, witnessing the cosmic dawn when the first stars ignited in the dark, and analyzing the chemical signatures of atmospheres on Earth-like planets orbiting distant suns. We may find the chemical fingerprint of life on a world 1,000 light years away simply because we finally have a clear enough view to look. The moon is not just a place to live. It is a place to see, a silent, dark, and perfect vantage point from which to map the architecture of the cosmos. When we build the first great lunar observatories, we will finally see the universe in its true, raw state. We will move from being a species that looks up from the bottom of a hazy well to a species that stands on the rim, looking out into the infinite. If something goes wrong, a sudden medical emergency that exceeds the colony's surgical capabilities, a critical hardware failure in the primary oxygen scrubbers, or an unforeseen psychological breakdown, help, or at least a path home, is relatively close. This proximity allows us to take risks that we wouldn't dare take on a 2-year round trip to Mars. On Mars, if a critical system fails, you must fix it or perish. On the moon, you can fail, you can learn, and most importantly, you can iterate. The moon allows us to build a culture of resilient engineering where we can test the limits of our technology without betting the entire species on a single mission. The moon also allows the first spacers to adjust to the crushing reality of the vacuum while maintaining a visual tether to their origins. For a lunar colonist, outside is a lethal environment, a silent world of radiation and extreme temperatures. Yet, when they look up through the reinforced glass of a cupola, they see their home planet hanging large, bright, and impossibly blue in the velvet blackness. This Earth view is a powerful psychological stabilizer. It prevents the sense of cosmic loneliness that is expected to plague the first Martian pioneers, for whom Earth will be nothing more than a faint, indistinguishable blue star. The moon allows us to gradually wean ourselves off the planetary surface. It is the place where we learn to live in a world of manufactured air and recycled water, while still being able to see the garden from the window. When we eventually do send the first crew to Mars, they will not go as the wide-eyed explorers of the 1960s. They will go with the cold, quiet confidence of a species that has already mastered the lunar environment. They will not be Earthlings in a foreign land. They will be spacers moving to a new district. The first Martian expedition will use the same habitat modules that have withstood decades of lunar dust. They will rely on the same radiation shielding composites that have protected lunar children from solar flares. And they will drink from the same water recycling systems that have been refined to perfection in the Shackleton crater. The moon is the crucible, where the Earthling is forged into the solar citizen. It is where we shed our terrestrial skin, our dependence on the passive hospitality of nature, and accepts the responsibility of creating our own world. In the lunar lava tubes, we will develop new traditions, new slang, and new ways of perceiving time. We will stop identifying as inhabitants of a country and start identifying as stewards of the light by conquering the moon. We prove to ourselves that we are no longer tethered to a single world. We demonstrate that our intelligence is not a local phenomenon of the Earth, but a universal force capable of thriving in the void. We prove that the cradle was just the beginning and necessary starting point, but not a final destination. The footprints we leave on the moon today are the foundation of the cities we will build on Mars tomorrow. We are no longer a species waiting for the next extinction event. We are a species taking control of its own timeline. The Silver Sentinel has finished its watch. Now, it is time for us to take ours. To complete the final movements of this 10,000-word manuscript, we expand on the economics of proximity and the industrial alchemy of low gravity. This section details how the moon acts as both a protective, training wheels environment for humanity and a high-tech foundry for the next generation of terrestrial and celestial products. The moon's proximity a mere 3-day journey across the translunar coast makes It is an ideal location for testing and developing the critical systems that will eventually sustain life in the far reaches of the solar system. In the unforgiving hierarchy of space travel, distance is synonymous with risk. If a primary life support system fails on a transit to Mars, the crew is months, perhaps even years, away from any hope of rescue or resupply. In deep space, time is the one resource you cannot manufacture. However, the moon is close enough to be within our reaction zone, offers a 3-day safety margina, period short enough to survive on emergency reserves, but long enough to demand that our systems be robust, self-reliant, and capable of autonomous repair. This 3-day bridge allows us to iterate on habitat design, closed-loop life support, and emergency medical protocols with a safety net that no other celestial body can provide. We go to the moon to fail safely so that we can succeed on Mars permanently. It is the only place in the cosmos where we can test the limits of human endurance while keeping the lifeboats within reach. Because of this accessibility, the moon becomes more than a survival camp. It becomes the premier laboratory for what economists are calling the microgravity renaissance. It offers a low-gravity environment 1/6 of Earth's that is perfect for material processing. Experiments that are physically impossible on our home planet, on Earth. Gravity is a constant interloper in the manufacturing process. It causes convection, the uneven rising of heat and sedimentation, the settling of heavier particles, both of which interfere with the delicate formation of molecular structures. In the stable, low-gravity environments of lunar labs, we can achieve a level of atomic-level precision that is the dream of every materials scientist. In these lunar foundries, we can manufacture ultra-pure fiber optics, such as Zeppelin, which can transmit data over vast distances with virtually no signal loss. A feat impossible in Earth's gravity, where impurities settle during the cooling process. We can cultivate superior pharmaceuticals, growing large, perfect protein crystals that allow researchers to design more effective drugs for cancer and neurological disorders. We can create exotic metal alloys, blends of elements that refuse to mix on Earth but combine perfectly in the lunar void, resulting in materials that are lighter than plastic but stronger than titanium. These are not merely scientific curiosities. They are high-value exports. A single kilogram of high-purity optical fiber or a specialized lunar-grown protein can be worth more than its weight in gold. These products create a self-sustaining economic loop. The profits from made on the moon. Exports can pay for the very oxygen, water, and infrastructure required by the colony. This shifts the narrative of space colonization from one of expenditure to one of investment. Moon ceases to be a drain on terrestrial taxpayers and becomes a profit-generating hub of the global economy. By leveraging the unique physics of 1/6 gravity, the moon provides the capital, both intellectual and financial, required to fuel our further expansion toward the asteroid belt and beyond. We are using the physics of the neighbor to fund the journey to the stars, beyond industry and survival. The moon offers a stable, vibration-free platform for astronomical observatories, free from Earth's atmospheric interference. For as long as humans have looked at the stars, we have done so through a veil. Our atmosphere, while essential for life, is a chaotic fluid that distorts our vision. Astronomers on Earth must contend with seeing the shimmering of the air caused by temperature fluctuations that blurs the light of distant stars. Even our most advanced adaptive optics are merely a filter, trying to correct for a fundamentally noisy medium. Furthermore, we are increasingly blinding ourselves. The modern astronomer faces the twin plagues of light pollution from sprawling megalopolises and the ever-growing swarm of satellite constellations that streak across long exposure images like digital scars. The moon, by contrast, is the ultimate sanctuary for light. It has no atmosphere to blur the incoming photons and no sky glow to hide the faintest, oldest galaxies in the universe. On the moon, the stars do not twinkle. They burn with a steady, unwavering brilliance. By placing telescopes in the lunar craters specifically at the poles where temperatures remain constant and cryogenic, we can observe the universe in wavelengths that are normally absorbed or reflected by Earth's ozone layer and water vapor. Much of the universe's story is written in the ultraviolet and infrared spectrums, portions of the light scale that the Earth's atmosphere effectively mutes. Lunar-based observatories can see the invisible universe. We can build gargantuan liquid mirror telescopes spinning vats of reflective fluid in the lunar low gravity that would collapse under their own weight on Earth, because the moon is geologically quiet compared to the Earth. These instruments can maintain a level of sub-millimeter precision for decades. These lunar eyes will allow us to look back to the very dawn of time, witnessing the cosmic dawn when the first stars ignited in the dark, and analyzing the chemical signatures of atmospheres on Earth-like planets orbiting distant suns. We may find the chemical fingerprint of life on a world 1,000 light years away simply because we finally have a clear enough view to look. The moon is not just a place to live. It is a place to see, a silent, dark, and perfect vantage point from which to map the architecture of the cosmos. When we build the first great lunar observatories, we will finally see the universe in its true, raw state. We will move from being a species that looks up from the bottom of a hazy well to a species that stands on the rim, looking out into the infinite. This clarity of vision will do more than provide data for textbooks. It will provide a sense of place. When we can see the beginning of time and the shores of other solar systems with crystal clarity, the petty divisions of Earth will seem even more insignificant. The moon provides the long view that our species has always lacked. It turns the universe from a mystery into a neighborhood. For decades, we viewed the moon through the lens of the Apollo missions, a magnificent desolation, bone-dry, dead, and utterly devoid of the volatiles required for life. This perception shaped our early space policy, framing the moon as a place to visit but never to stay. However, the discovery of billions of tons of water ice transformed our strategy overnight. It was as if a traveler in a vast desert suddenly discovered a deep, hidden aquifer beneath the dunes. Crucially, the lunar poles harbor what may be the most valuable substance in the solar system: vast reserves of water ice. This ice is hidden in the permanently shadowed regions, PSRs, of craters like Shackleton basins, so deep and positioned at such an angle that the sun has not shone on their floors for billions of years. In these natural cold traps, temperatures hover around 230 degrees Celsius, preserving water that may have been delivered by cometary impacts during the early formation of the solar system. This ice is a game changer. It is the chemical foundation upon which a spacefaring civilization will be built. This ice is far more than just a drink for thirsty astronauts. It is the raw material for the first off-world industrial revolution. To unlock its potential, we utilize the oasis of physics found at the poles. While the crater floors are in eternal darkness, the nearby rims, often called the peaks of eternal light, receive near-constant solar illumination by placing massive solar arrays on these peaks. We generate a steady stream of electricity to power the robotic miners in the dark below. Through the process of electrolysis, the harvested ice is melted and subjected to an electric current, splitting the H2O molecule into its constituent parts, hydrogen and oxygen. This simple chemical reaction provides the three pillars of survival: potable water, purified for human consumption and sanitation. Breathable. Oxygen, circulated through the pressurized habitats to sustain a growing population. Rocket. Propellant. When cooled into liquid form. Hydrogen and oxygen become the most potent chemical propellant available to modern engineering. Most importantly, liquid hydrogen and liquid oxygen are the primary components of high-performance rocket fuel. In the traditional Earth-centric model of spaceflight, we must carry every gram of this fuel out of Earth's deep gravity well. This is the gravity tax, the massive, energetic penalty we pay for starting our journey on a heavy planet. Imagine fueling missions to Mars and the asteroid belt directly from the Moon by shifting our refueling operations to the lunar surface. We effectively move our launch pad to the top of the gravitational hill. A ship departing from the Moon requires significantly less energy to reach escape velocity than one departing from Earth. This drastically reduces the launch mass of every mission. Instead of a rocket that is 90% fuel just to get off the ground, we can build leaner, more efficient vessels designed for the deep space coast in this new logistical framework. The Moon becomes the Suez Canal of the solar system, the essential waypoint that makes the rest of the journey possible. It is the hub where the deep well traffic from Earth meets the shallow well traffic of the rest of the system. The Moon provides the propellant that allows us to move heavy cargo to Mars, to send robotic harvesters to the belt, and to maintain a permanent human presence in the Lagrange points. It is the logistical anchor that turns space travel from a series of one-off expeditions into a sustainable, repeatable transport system. Without lunar water, we are a species tethered to our home. With it, the entire solar system becomes accessible. The Moon provides not just the energy and fuel for our journey, but the very materials needed to build our new home. For decades, the primary constraint of space exploration was the mass limit, the reality that every gram of shielding, every structural beam, and every floor plate had to be manufactured on Earth and hauled up the expensive incline of our gravity well. This made space habitats fragile, cramped, and temporary. But the lunar regolith, a fine, gray layer of dust and broken rock created by eons of micrometeorite impacts, is an abundant resource that fundamentally changes the architecture of the void. We no longer need to dream of hauling heavy steel beams and concrete from Earth. Instead, we will use the ground beneath our feet. We are transitioning from the era of bringing our own tents to the era of quarrying our own cities. Using advanced 3D printing technology and microwave sintering, we can turn this loose volcanic dust into solid structural components. Lunar regolith is rich in iron and silicon, materials that respond remarkably well to heat. By applying concentrated microwave energy or high-powered lasers to the dust, we can sinter it, melting the edges of the particles so they fuse into a hard, ceramic-like substance. This is the birth of Insight to Resource Utilization, ISRU, in its most physical form. Autonomous robotic printers, resembling a cross between a bulldozer and a high-tech weaver, will crawl across the lunar surface. These machines will scoop up the raw regolith, process it through an internal heating chamber, and extrude it as a viscous lunar concrete, layer by layer. These robots will build structures that are literally part of the Moon itself. One of the greatest threats to long-term human health in space is cosmic radiation and solar particle events. On Earth, we are protected by miles of atmosphere and a robust magnetic field. On the Moon, we have neither. To survive, we need mass. By 3D printing habitats with walls several meters thick using the abundant regolith, we provide natural protection against the relentless bombardment of high-energy particles. These thick, sintered shells also act as a thermal buffer. insulating the interior from the extreme temperature swings of the lunar day, which can fluctuate from 120 degrees Celsius in the sun to 170 degrees Celsius in the shade. We aren't just building houses. We are building vaults. Beyond habitats, the regolith revolution allows us to build the infrastructure of a functioning economy. We can print landing pads that are smooth and vitrified, ensuring that the exhaust from arriving rockets doesn't kick up plumes of jagged, abrasive dust that could damage nearby equipment. We can print paved roads that connect distant mining outposts to the central hub, allowing robotic rovers to move at high speeds without the risk of getting bogged down in the soft lunar soil. This ISRU capability is the key to true independence. By reducing the need to transport everything from Earth, we finally break the umbilical cord of the mother planet. We move from being explorers dependent on a fragile supply chain to being settlers who own the means of their own survival. When we look at a 3D printed lunar city, we see the first true human footprint that isn't just a mark in the dust, but a permanent alteration of the landscape. We are learning to work with the universe rather than against it. By the time we have mastered the art of building with regolith, we will have the skills necessary to build on the rust plains of Mars and the icy surfaces of the outer moons. We will have proven that humanity can take any raw material the cosmos provides and turn it into a home. While the moon is our gateway, it is a gateway guarded by the most hostile conditions humanity has ever faced. To live there is to exist in a state of constant, high-stakes engineering, where the margin for error is measured in millimeters of pressure seal and minutes of oxygen. Unlike Earth, which swaddles us in a thick, protective atmosphere and a powerful magnetic shield, the magnetosphere, the moon is naked to the cosmos. It sits exposed, a silent witness to the raw violence of the sun and the deep space radiation that our birth world filters out. So, this lack of a shield is the primary architect of lunar life. On Earth, we are used to an environment that is passively hospitable. The air stays breathable, the pressure stays stable, and the radiation stays manageable without any conscious effort on our part. On the moon, hospitality must be actively manufactured. The moon lacks any defense against the invisible rain of ionizing radiation from the sun and high-energy cosmic rays from the distant corners of the galaxy. For a lunar inhabitant, a solar flare is not a beautiful auroral display or a minor disruption to satellite TV. It is a lethal, hard radiation event. To overcome this, the architecture of the moon will not follow the terrestrial tradition of glass and steel towers that reach for the sky. Instead, it will be an architecture of depth, density, and retreat. Future lunar bases will likely be subterranean, utilizing the natural geography created by the moon's volcanic youth. Billions of years ago, as the moon cooled, rivers of molten basalt carved out vast lava tubes, underground cathedrals of rock that can span hundreds of meters in width. These tunnels offer a ready-made sanctuary. By nestling our habitats within these ancient tubes, we gain an immediate and nearly impenetrable shield against the cosmic environment. By mastering the inflatable volume and the closed-loop biosphere, we prove that human life is not a parasite of the Earth, but a gardener of the universe. We prove that we can take the sterile elements of the cosmos, sunlight and rock, and weave them into a living tapestry. This mastery is the final prerequisite for the long journey to Mars. If we can make the moon bloom, we can make any world a home. Perhaps the most daunting logistical hurdle of lunar life is the 2-week night. Because the moon is tidally locked to its orbit around the Earth. Its rotational period is nearly 28 Earth days. For a colonist at the lunar equator, this results in a brutal cycle. 14 days of unrelenting, high-intensity sunlight followed by 14 days of absolute, freezing darkness, This is not merely a matter of turning on the lights. On Earth, our atmosphere and oceans act as a thermal battery, retaining the sun's heat long after dusk. On the moon, the lack of an atmosphere means that the moment the sun dips below the horizon, the temperature collapses from a blistering 127 degrees Celsius to a lethal chill of minus 173 degrees Celsius. This is the lunar night survival problem. To maintain the life support systems, heavy-duty heaters, and industrial robots during this period, we cannot rely on the energy of the sun alone. To survive the night, we must move beyond the solar monoculture, a massive battery, arrays and regenerative fuel cells which store energy by turning water into hydrogen and oxygen during the day and recombining them at night will handle short-term surges and emergency backups. They are insufficient to power a city for 350 hours of darkness. The mass required for a battery bank large enough to support a heavy industrial colony would exceed the carrying capacity of our largest rockets. The heartbeat of the lunar base will, therefore, be small modular fission reactors, SMRs. These are not the massive, sprawling nuclear plants of the 20th century. Instead, they are compact, self-contained, and inherently safe units that can be transported in a single rocket fairing. These reactors use advanced liquid metal or gas cooling systems and are designed to be plug-and-play. These reactors are the true engines of the outpost. They provide a continuous high-output power source that is entirely independent of the solar cycle, while the solar arrays positioned on the peaks of eternal light provide the massive surges of energy needed for heavy mining and electrolysis during the lunar day. The nuclear reactors provide the baseline, metabolic rate of the colony. They ensure that when the sun goes down and the temperature drops to its lethal floor, the lights stay on, the oxygen scrubbers continue to hum, and the thermal heaters keep the habitat's interior at a comfortable shirt-sleeve temperature. This combination creates a hybrid energy grid, a redundant, resilient system that mirrors the energy security we enjoy on Earth. This energy independence transforms the moon from a tent in the desert into a permanent, thriving city that never sleeps, even when the sun is on the other side of the world. Mastering nuclear power on the moon is a vital prerequisite for the rest of the solar system. As we move further from the sun toward the asteroid belt, the moons of Jupiter, and the rings of Saturn, the solar flux, the intensity of sunlight drops off according to the inverse square law. By the time we reach Jupiter, the sun is 25 times fainter than it is on Earth. By the time we reach Pluto, it is nearly 1,000 times fainter. To be a solar system civilization, it cannot be solely dependent on the sun. We must carry our own stars with us in the form of nuclear energy. The moon is where we learn to manage this power safely and efficiently, ensuring that wherever humanity goes, we carry the light with us by establishing ourselves on the moon, Mars, and the vast reaches beyond. We are performing the ultimate act of stewardship. We often think of space travel as a purely technological feat, but it is, at its heart, a biological imperative. We are the current torchbearers of a flame that was ignited 4 billion years ago, the primordial oceans of Earth. Since that first spark, life has undergone a relentless, agonizing struggle to survive, to adapt, and to perceive the evolution of the eye, the heart, and the complex architecture of the mind was not a random sequence of events meant to end in the dust of a single planet. It was a climb. We are ensuring that this struggle was not in vain. We are taking the light of reason, the unique ability of the universe to look back at itself and ask one, carrying it into a cosmos that is, as far as we know, silent and dark. Without consciousness to witness it, the universe is merely a cold machine of ticking atoms. With us, it becomes a story. We are moving from being a species, that is of a world to a species that is of thee. Stars, this transition is the great maturity. It is the moment. We stop being a passenger on a planetary vessel and start being the navigators of our own destiny. This journey will be difficult. It will be staggering in its expense and, at times, heartbreaking in its danger. There will be setbacks. There will be missions that do not return, and pioneers whose names will be etched into the silent stone of the moon. But we must weigh these costs against the alternative. The cost of staying is far higher than the cost of going. To stay is to wait for the inevitable stroke of cosmic or self-inflicted misfortune. To go is to seize the infinite. We are moving from the Malthusian trap of finite resources into the Kardashev scale of infinite energy as we build our first homes in the lunar dust and look back at the pale blue dot hanging in the velvet sky. We will realize a profound truth. We didn't leave Earth to escape it. We left Earth to save it. By moving our heavy industries to the moon, our mining to the asteroids, our energy production to the sun-soaked orbits of the inner system, we allow our birth world to breathe. We return the Earth to its rightful status as a garden, a sanctuary, and a protected heritage site for all of biology. In the silence of the lunar night, we will finally understand Earth's true value. We will fulfill our potential not as consumers of a planet, but as citizens of the solar system. Our story is no longer written in the dirt of a single world, vulnerable to the wind and the rain. It is written in the light of 100 billion suns. The frontier is not a place. It is a state of being. It is the refusal to accept a ceiling on human potential. As the first lunar cities begin to glow on the dark limb of the moon, and the first Martian greenhouses turn the red soil green, we will know that we have passed the great filter. We have become a multi-planetary species. The cradle is behind us. The universe is open. The journey has begun. A permanent lunar presence will do more than sustain a few scientists. It will foster a burgeoning lunar economy, the likes of which has never been seen in human history. We are moving past the era of exploration for exploration's sake and into the era of the lunar marketplace. Beyond the critical extraction of ice and metals, the moon will host a diverse array of commercial interests. Private research facilities will lease space to develop life-saving pharmaceuticals in the unique low-gravity and high-vacuum environment. Universities will establish permanent campuses to study the 4-billion-year history of the solar system, preserved perfectly in the airless lunar crust. As the infrastructure matures, we will see the birth of the most exclusive industry of the 21st century, space tourism. While it may begin as a luxury for the ultra-wealthy, the development of reusable lunar landers and modular hotels will eventually bring the sublime beauty of the Earthrise to a broader segment of humanity. This is not just about vacations. It is about the overview effect, the profound shift in consciousness that occurs when a human looks back at their home planet and sees it as a single, borderless, and fragile entity. This shift will become a major cultural export of the moon, fueling a new era of global unity on Earth beyond the physical economy. The moon will become our most crucial testbed for human adaptation. We are biological creatures designed for 1 gram Earth gravity. To live on the moon is to exist in 0.16 grams. We need to understand the long-term effects of this environment on the human heart, the density of our bones, and the development of the next generation. The moon provides the perfect laboratory for this biosocial experiment. Furthermore, the moon will teach us how to survive the psychological toll of long-duration habitation. Living in a confined, artificial environment where outside is a lethal vacuum requires a new kind of mental resilience. We will develop the social structures, the entertainment, the communication protocols, and the conflict resolution strategies necessary for a healthy society. These human systems are just as important as the life support machines. If we can build a happy, stable, and thriving community on the moon, we will have the psychological blueprint for the years-long journey to Mars. Most importantly, the moon will serve as a vital staging post for deeper space missions. The grand central station of the inner solar system. For 60 years, we have been limited by the tyranny of the rocket equation, which dictates that we must carry the fuel required to carry the fuel. By moving our departure point to the moon, we break these chains. Instead of launching a massive multi-billion-dollar mission from Earth's deep gravity well, payloads and personnel will rendezvous at a lunar spaceport. These astronauts will travel from Earth in high-efficiency taxis, while the heavy supplies, fuel, and shielding will be waiting for them in lunar orbit, manufactured or harvested on the moon itself. These ships will refuel with lunar hydrogen, stock up on lunar-grown food, and embark on journeys to Mars, the asteroid belt, and the Jovian moons with a fraction of the energy previously required. This staging post transforms the inner solar system from a collection of unreachable islands into a connected neighborhood. It opens the door to the belt economy and the eventual colonization of the red planet, ensuring that the human story is no longer confined to a single chapter, but is a sprawling, multi-world epic. In the final analysis, the colonization of the moon and the subsequent expansion into the solar system is the fulfillment of our highest potential. We began as a species that looked at the stars and told stories. We are becoming a species that lives among them. The moon is the bridge. It is the place where we learn to be spacers, where we prove our tech, where we find the resources to fuel our ambition. As we look up from the Earth today, we see a cold gray rock. But tomorrow's children will look up and see the lights of cities. They will see the flickering thrusters of ships departing for the Martian frontier. They will see a future where humanity is a resilient, multi-planetary species, no longer a victim of terrestrial fate, but the architect of its own cosmic destiny. We go not because the Earth is small, but because the universe is large. And we have finally found the courage to claim our place within it. From the first footprint at Tranquility Base to the first city in the lunar peaks, we are taking the most important step in our history. We are coming home to the stars. Mars. The red planet has captivated humanity for centuries, occupying a singular and prestigious place in our collective imagination. Long before the first telescope allowed us to resolve its dusty plains, Mars was the god of war, a wandering spark in the night sky that seemed to burn with a visceral internal fire. But as our instruments sharpened and our probes began to peel back the veil of the Martian atmosphere, we found something far more profound than a myth. We found a reflection of our own home. Mars is more than a destination. It is a mirror. It is the only other world in the solar system where a human could stand and see a horizon that feels familiar. Its tantalizing similarities to Earth are not merely poetic. They are the fundamental building blocks of a viable colony. A Martian day, or sol, is roughly the same length as an Earth day, approximately 24 hours and 37 minutes. This is a biological gift of unimaginable value. It means that the circadian rhythms of humans, animals, and plants, which evolved over billions of years to follow a 24-hour cycle, can be transplanted to Mars with minimal disruption. On the moon, the 2-week-long day and night cycle is a brutal environmental hurdle. On Mars, the sun rises and sets with a comforting terrestrial rhythm. This similarity provides the psychological and biological foundation upon which a permanent civilization can be built. The lure of Mars deepens when we look at its geology. Like Earth, Mars possesses polar ice caps, vast, shimmering expanses of frozen water and carbon dioxide. Beneath its rust-colored regolith, there is overwhelming evidence of a watery past. Ancient riverbeds, sprawling deltas, and minerals that only form in the presence of liquid water. We now know that Mars, was once a world of blue oceans and thick clouds. While that world is currently dormant, the bones of a biosphere remain. This presence of water ice is the gold of the Martian frontier. It is the source of life, the precursor for agriculture, and the raw material for the rocket fuel that will eventually power the return journeys to Earth. Furthermore, Mars possesses an atmosphere. Though it is thin, less than 1% of Earth's pressure and composed primarily of carbon dioxide, its presence is a strategic advantage. It provides a measure of protection against micrometeorites and some solar radiation. More importantly, it is a chemical warehouse. Through the Sabatier reaction, we can combine Martian CO2 with hydrogen to create methane and oxygen. This means Mars is not just a place we visit. It is a place where we can live off the land. We can breathe the air. We manufacture from the sky and fuel our return ships from the very atmosphere that surrounds them. While Mars is the prime candidate for colonization, we must be clear-eyed about the scale of the endeavor. Establishing a self-sustaining civilization on Mars represents humanity's next giant leap into the cosmos. And it is a leap that is far more challenging than the Moon. The Moon is a 3-day journey. Mars is a 6 to 9 month voyage across a cold, radiation-drenched void. On the Moon, if a critical component fails, help is a few days away. On Mars, you are on your own. There is no rescue. There is no abort to Earth. The distance creates a communications lag, a delay of up to 24 minutes each way, which means that a Martian colony must be fundamentally autonomous. They cannot wait for instructions from Houston or London to solve an emergency. They must be their own engineers, their own doctors, and their own governors. This distance will forge a new kind of human culture, the Martian, defined by extreme self-reliance, technical brilliance, and a communal bond that is forged in the fires of shared survival. The difficulty of the journey is the very thing that will ensure the strength of the civilization. The transition from a base to a civilization on Mars will be the most complex logistical undertaking in history. The first habitats will likely be the landers themselves, followed by modular units connected by pressurized tunnels. But as the population grows from dozens to thousands, the architecture must evolve. We will move into the bunker era, utilizing the natural protection of Martian lava tubes, vast subterranean cathedrals formed by ancient volcanic activity. Within these tubes, we can build entire cities. Shielded from the surface's radiation and dust storms, these cities will be the pinnacle of human ingenuity. They will feature vertical farms that utilize the Martian soil once scrubbed of toxic perchlorates and artificial lighting to grow a diverse diet of earthborne crops. They will have closed-loop economies where every scrap of metal and every liter of water is accounted for. But more than that, they will be places of beauty. To live on Mars is to live with a different aesthetic, the salmon-colored sky at noon and the blue sunsets at dusk. We will build parks under domes, libraries filled with the digitized knowledge of Earth, and schools where the first true Martians will learn about the distant, blue planet where their ancestors once lived. As we establish this self-sustaining civilization, we will face profound ethical and philosophical questions. Do we have the right to terraform Mars, to intentionally alter its atmosphere to make it more Earth-like? If we find even the simplest microbial life in the Martian deep subsurface, does that planet belong to them or to us? These are the questions that will define the 22nd century. Colonizing Mars is not just about survival. It is about the moral expansion of humanity. It forces us to reconsider our relationship with planetary biospheres and our responsibilities as a multi-planetary species. By building a society on Mars, we aren't just duplicating Earth. We are attempting to build a better version of it. We are taking the lessons learned from our terrestrial mistakes, lessons in sustainability, cooperation, and environmental stewardship, and applying them to a fresh canvas. Mars is our second chance. It is the giant leap that ensures that if something should happen to the cradle, the child of humanity will still endure. Thriving among the stars, Mars offers more than just scientific curiosity. It offers a future. It has a thin atmosphere, primarily carbon dioxide, which can be processed to create oxygen and rocket fuel. Critically, it possesses vast quantities of water ice, particularly at its poles and beneath the surface, essential for drinking, agriculture, and fuel production. Its milder gravity, about one-third of Earth's, is more forgiving for human physiology than the Moon's. The sheer scale of Mars also makes it appealing. It's a planet with diverse terrain, vast plains, colossal canyons, and towering volcanoes, offering immense potential for future expansion. A thriving Martian civilization could serve as a second home for humanity, a vital redundancy in the face of existential threats on Earth. The journey to Mars is arduous, lasting 6 to 9 months, depending on orbital alignments. This presents significant challenges: prolonged exposure to space radiation, the psychological toll of isolation, and the physiological effects of microgravity, including bone density loss and muscle atrophy. Future Mars missions will require advanced propulsion systems, such as nuclear, thermal, or electric propulsion, to shorten transit times. Spacecraft will need robust radiation shielding and sophisticated closed-loop life support systems. Onboard gravity solutions like rotating sections for artificial gravity could mitigate physiological decay. Automated landing systems capable of precisely delivering massive payloads, habitats, equipment, and supplies will be crucial before humans even arrive. Initial Martian settlements will likely be partially underground or heavily shielded to protect against radiation, micrometeoroids, and extreme temperature fluctuations. Inflatable modules similar to those on the Moon will be augmented with sturdy Martian materials. Water ice will be mined and processed, and the carbon dioxide atmosphere will be converted into oxygen. Using technologies like the MOXIE instrument on the Perseverance rover, agriculture will be conducted in pressurized greenhouses. Using hydroponics or aeroponics, creating vital fresh food and recycling air. Energy will primarily come from vast solar arrays, potentially supplemented by small nuclear fission reactors to ensure continuous power during dust storms and the long Martian night. The focus will be on self-sufficiency, reducing reliance on Earth for critical supplies. The ultimate dream for Mars is terraforming, transforming it into a more Earth-like world. This is a monumental, multi-generational endeavor, but the concept is tantalizing. Initial steps could involve releasing greenhouse gases to warm the planet, sublimating the CO2 ice at the poles, which would thicken the atmosphere and allow liquid water to flow. Eventually, genetically engineered extremophiles could be introduced to begin converting the atmosphere and enriching the soil. While a fully breathable, Earth-like atmosphere and vast oceans are millennia away, even partial terraforming could make Mars significantly more hospitable, paving the way for open-air living and a dramatically expanded biosphere. It's a testament to humanity's long-term vision, a project that transcends individual lifetimes. While planets offer gravity and vast landmasses, the inner solar system's true wealth lies hidden in the asteroid belt and beyond. These rocky remnants from the early solar system are not just potential threats. They are immense repositories of resources. Coupled with this, the concept of living in space itself, vast orbital habitats, offers another pathway to human expansion. Asteroids are incredibly diverse. C-type carbonaceous asteroids are rich in water, organic compounds, and volatile materials, essential for life support and fuel. S-type stony asteroids contain silicates and nickel iron, M-type metallic asteroids are the most valuable. Packed with iron, nickel, cobalt, and platinum group metals like platinum and iridium. A single metallic asteroid could contain more platinum than has ever been mined on Earth, potentially worth trillions of dollars. Mining these resources would revolutionize Earth's economy, provide abundant materials for constructing habitats and spacecraft in space, and virtually eliminate resource scarcity as a limiting factor for expansion. The technologies would involve advanced robotics, autonomous mining rigs, and efficient processing facilities, all operating in Merav Ravid. The low gravity of asteroids makes them ideal for insight to resource utilization, ISRU, and manufacturing. Imagine factories built directly on or within asteroids, processing raw materials into structural components, rocket fuel, and even complex devices. These asteroid mining outposts would become crucial hubs, fueling deep space missions and constructing massive orbital habitats without the need to lift materials out of Earth's gravity well. The energy for these operations could come from solar power or even small nuclear reactors. This off-world manufacturing capability would dramatically reduce the cost and complexity of space exploration, creating a truly self-sufficient space economy. While planets offer gravity, orbital habitats offer scalability and control. Concepts like the O'Neill cylinders or Stanford toruses are visionary designs for rotating space colonies that can house thousands, even millions of people. These enormous structures would spin to create artificial gravity, allowing for normal human life, complete with homes, parks, and even agriculture. They would be self-contained ecosystems, recycling air, water, and waste. Positioned in stable orbits, perhaps around Earth, the Moon, or even at Lagrange points. These habitats could be built using materials sourced from the Moon and asteroids. They offer a future where humanity isn't limited to planetary surfaces, but can expand into a vast network of spaceborne civilizations, each with its own unique environment and culture. These are not just space stations. They are truly new worlds created by human ingenuity. While the inner solar system offers our immediate goals, the gas giants and their icy moons in the outer solar system present even grander, albeit more distant possibilities. These worlds, once considered too remote and hostile, are now being re-evaluated as potential future frontiers. Moons like Europa, Jupiter, and Enceladus Saturn are of profound interest. Beneath their thick ice shells lie vast liquid water oceans, warmed by tidal forces from their giant planets. These oceans are prime candidates for harboring extraterrestrial life. And future robotic probes, perhaps even human-operated submersibles, could explore these alien depths. Beyond the search for life, these moons contain vast quantities of water, a critical resource for future expansion. Titan, Saturn's largest moon, is unique with its thick nitrogen atmosphere, methane lakes, and complex organic chemistry. Future missions could involve floating research stations on its methane seas, exploring a world that resembles early Earth in many ways, albeit at frigid temperatures. These worlds represent a new frontier for astrobiology and resource extraction. Even the gas giants themselves hold immense potential. Jupiter and Saturn are rich in hydrogen and helium, including the rare isotope helium-3, a theoretically clean and highly efficient fuel for future fusion reactors. While challenging technologies for atmospheric mining could one day harvest these resources. Further out, beyond Neptune, lies the Kuiper Belt, a vast region of icy bodies. These distant worlds are essentially enormous frozen reservoirs of water, methane, ammonia, and other volatiles, the building blocks of life and fuel. They could become vital sources of materials for constructing future interstellar probes or for long-duration human outposts, extending humanity's reach to the very edge of our star system. The journey to these worlds would be long, requiring breakthroughs in propulsion. But the resources are almost limitless, from the first flickering campfires to our potential future as a multi-planetary species. Humanity's journey has been one of constant expansion and discovery. The colonization of the solar system is not just a scientific endeavor, it is a cosmic imperative. It's about securing our long-term survival, fostering unprecedented innovation, and providing a boundless future for generations to come. We are a species driven by curiosity, resilience, and the relentless pursuit of knowledge. These are not merely traits we possess. They are the core of our survival strategy. Throughout our history, whenever humanity has faced a closed door, we have found a way to pick the lock. When the climate shifted during the great ice ages, we didn't perish. We invented fire and clothing. When the oceans seemed like impassable barriers, we built vessels to ride the swells. This resilience is our greatest export as we leave the Earth. We are taking with us a biological heritage of overcoming the impossible. The solar system awaits, a vast canvas for our future. And though it is painted in the cold blacks of the vacuum and the harsh reds of Martian dust, it is a canvas that will eventually bear the unmistakable colors of human life. The challenges of this expansion are indeed immense, staggering, even to our current way of thinking. We must learn to navigate the silent, invisible lethality of cosmic radiation. We must master the art of artificial gravity and closed-loop biospheres. We must solve the psychological riddle of being millions of miles from the mother world. But history has shown that the scale of a reward is always proportional to the difficulty of the challenge. The rewards of the solar system are not just the tons of platinum from asteroids or the liters of water from the moon. The true reward is the metamorphosis of the human spirit. By embracing this grand adventure, we are forced to shed our parochialism, short-term thinking, and our ancient tribalisms. In the vacuum of space, the differences between us vanish, replaced by the singular, unifying necessity of being human. By colonizing new worlds, we will do more than just build habitats. We will redefine what it means to be human. For all of history, human has been synonymous with earthling. We have defined our biology by Earth's gravity, our vision by Earth's light, and our culture by Earth's seasons. But as the first generation of children is born in the low gravity of Mars, or the rotating cylinders of O'Neill colonies, the definition will expand. We will see the rise of the Homo cosmicus, a version of humanity that is physically more adapted to low gravity, intellectually more attuned to systems thinking, and philosophically more aware of the fragility of life. This redefinition is not a loss of our Earthness, but an evolution of it. We are taking our rightful place among the stars, moving from being the accidental inhabitants of a single planet to being the intentional stewards of a solar system. We are becoming the bridge through which the universe seeks to know itself. Without consciousness, the beauty of Saturn's rings or the majesty of Olympus Mons are merely arrangements of matter and light in the dark. By being there, by witnessing them, and by building our homes among them, we give the cosmos a voice. We transform the void into a place, and the vacuum into a home. As we stand at this historical crossroads, looking out from the rim of our home world, we must realize that the final frontier is not just a destination, it is our destiny. It is the logical conclusion of a journey that began when the first eyes looked upward and wondered about the nature of the wandering stars. We are the ancestors of a future that will span the stars. The blueprints we draw today, the small outposts we build on the moon, and the first footprints we leave on Mars are the opening sentences of a new volume of human history, a volume that will never truly end. We go into the dark not to escape our problems, but to find our potential. We go because the same fire that burned in the hearts of the great explorers The same curiosity that drove the scientists of the Enlightenment, and the same resilience that allowed us to settle every corner of the Earth, is now pushing us toward the vertical frontier. We are ready. The technologies are converging, the resources are waiting, and the spirit is willing. The solar system is no longer a distant myth. It is our backyard. The stars are no longer just lights in the sky. They are the destinations of our descendants. We are humanity, the explorers, the dreamers, the survivors, and our journey has only just begun.